ancient mysteries rarely begin with answers. They begin with something that should not exist. A city hidden beneath layers of another civilization. A monument too massive for its environment. A structure aligned with patterns no one expected ancient people to track. Over time, discoveries like these have forced historians and archaeologists to repeatedly reconsider what early civilizations were truly capable of. Some mysteries were eventually explained, others only became stranger as more evidence appeared. And that is what makes the ancient world so fascinating. The deeper we investigate, the more the past stops looking primitive and starts looking unfamiliar. Not because ancient people were supernatural, but because much of their world has been lost, fragmented, or buried beyond recognition. What survives today may only be the edge of a much larger story. Anamurium sits on the southern coast of Turkey, facing the open Mediterranean where salt, earthquakes, humidity and pirate raids should have erased an ancient city long ago. But Anamurium refused to disappear. Beneath collapsing arches and silent bathhouses lies evidence of engineering, materials and chemical knowledge that still challenge archaeologists today. The ruins were first systematically documented in the 19th century, but major excavations accelerated during the 1960s under Canadian archaeologist Elizabeth Rosenbaum. What researchers uncovered was not just another Roman coastal settlement. They found one of the best preserved necropolises in Anatolia, sophisticated water systems, unusually durable building materials, and mosaics whose colours survived nearly 2 millennia of Mediterranean sunlight and sea air. The deeper excavations went, the stranger the city became. One of the first mysteries involves survival itself. Anamurium stands directly beside the sea in a region exposed to constant humidity and salt-laden winds. Modern reinforced concrete near coastlines can begin deteriorating within decades as chloride ions penetrate the material and corrode internal structures. Yet many of Anamurium's walls, cisterns and bath complexes remain structurally stable after nearly 1,700 years. Some Roman maritime concrete structures in Italy, such as those at Pozzuoli, are known to strengthen over time through chemical reactions involving volcanic ash and seawater. But Anamurium is hundreds of kilometers away from the major volcanic zones traditionally associated with that technology. Material analysis from comparable Roman coastal sites suggests builders may have used hydraulic lime mixtures containing pozzolanic compounds capable of forming rare minerals like aluminum tobermorite. These crystals increase resistance against cracking and chemical erosion. The mystery is logistical as much as chemical. If similar materials were used at Anamurium, where did they come from? Transporting specialized mineral additives across the Mediterranean would have required a remarkably organized maritime supply network at a scale historians once underestimated. The city's water system creates another puzzle. Southern Anatolia experiences long dry summers, yet Anamurium supported bathhouses, fountains, storage reservoirs, and a large urban population for centuries. Archaeologists mapped aqueduct gradients that remained astonishingly precise across uneven rocky terrain. In some sections, the slope variation is so minimal that even small errors would have stopped water flow or created destructive pressure surges. Modern gravity-fed water systems often rely on laser measurement tools to maintain similar consistency. Roman surveyors supposedly worked using simple instruments like the chorobates and groma, yet the hydraulic precision seen here rivals far later engineering systems. The mystery becomes more striking when compared to medieval Europe. In many medieval cities over 1,000 years later, sewage and water control systems remained primitive and inconsistent. Yet at Anamurium, centuries earlier, engineers maintained controlled water distribution in one of the Mediterranean's harshest coastal environments. This raises a disturbing possibility. Certain branches of practical engineering knowledge may have been partially lost after the collapse of the Roman world. The bathhouses reveal another unexplained achievement. Anamurium used hypercaust heating systems in which hot air circulated beneath raised floors and through wall cavities. Normally, coastal moisture and thermal expansion gradually destabilize these hollow floor systems. Modern concrete structures exposed to repeated thermal cycling often develop microfractures within decades. Yet portions of Anamurium's heated floors survived for over a millennium. Some structural engineers believe Roman builders may have unintentionally created early forms of flexible composite construction. Their mortar mixtures sometimes contain crushed ceramics, volcanic particles, lime, and varying aggregate sizes that distributed stress more efficiently than rigid modern cement. Ironically, some modern Portland cement structures degrade faster because they are too rigid under environmental stress. In certain ways, Roman materials behaved less like brittle stone and more like adaptive geological systems. Then there is the necropolis, one of the largest surviving Roman cemeteries in Anatolia. Hundreds of tombs spread across unstable coastal terrain vulnerable to erosion and seismic activity. Yet many remain standing despite centuries of earthquakes affecting the eastern Mediterranean. Geological studies suggest some structures distributed weight unusually well across softer soil layers instead of anchoring deeply into rigid foundations. Modern earthquake-resistant architecture often relies on controlled flexibility rather than absolute rigidity. Japanese seismic engineering, for example, allows buildings to absorb and redistribute movement rather than resisting it completely. The unsettling question is whether ancient builders discovered similar principles empirically through generations of observation. If so, Anamurium may preserve evidence of forgotten seismic adaptation techniques developed nearly 2,000 years before modern structural dynamics emerged as a scientific discipline. But perhaps the strangest mystery of all appears inside the city's surviving mosaics and pigments. At first glance, the mosaics seem merely decorative. Geometric floors, coloured stone patterns, fragments of wall paintings. But laboratory examinations reveal something deeply unusual about their durability. The Mediterranean climate is brutally destructive to pigments. Ultraviolet radiation breaks molecular bonds. Salt crystallization fractures surfaces internally. Humidity accelerates chemical reactions that bleach ancient colours. Even many medieval frescoes deteriorated rapidly under such conditions. Yet some pigments at Anamurium retained remarkable chromatic stability after nearly 2,000 years. Researchers studying Roman pigments across the Mediterranean identified compounds containing iron oxides, Egyptian blue, cinnabar, carbon black, and copper-based minerals capable of resisting extreme environmental degradation. Egyptian blue is especially mysterious. First synthesized over 4,500 years ago, it is considered humanity's earliest synthetic pigment. Modern scientists discovered that it emits infrared luminescence invisible to the human eye, a property now being explored for anti-counterfeit technologies and advanced imaging systems. What makes this disturbing is not merely that ancient civilizations created durable pigments. It is that some of these manufacturing methods remain incompletely understood even today. Reproducing exact ancient pigment compositions consistently has proven difficult because tiny variations in temperature, mineral purity, kiln atmosphere, and particle size dramatically affect the final chemical stability. At Anamurium, several mosaic fragments survived conditions that should have erased them centuries ago. In some protected areas, pigment adhesion remained unusually strong despite prolonged salt exposure. Certain mineral combinations appear to have formed microscopically stable crystalline bonds with plaster surfaces, reducing flaking and moisture penetration. In modern conservation science, researchers still struggle to develop restoration materials capable of matching the longevity of some Roman pigments. The comparison becomes even more uncomfortable when viewed against modern architecture. Many contemporary paints begin fading within years under ultraviolet exposure. Some modern coastal concrete structures require major restoration after only 50 to 100 years. Meanwhile, ancient pigments at Anamurium endured nearly 20 centuries of sea air, storms and heat, while preserving visible colour integrity. This pattern appears repeatedly across the ancient world. Roman concrete outlasting modern seawalls, Egyptian pigments resisting ultraviolet decay longer than industrial paints, ancient hydraulic systems maintaining stable gradients without electronic instruments. Again and again, archaeology uncovers technologies that seem primitive according to historical narratives, yet perform at levels surprisingly difficult to replicate. Do you think civilizations like Anamurium truly possessed engineering knowledge far beyond what history tells us? Or are modern scientists still underestimating the capabilities of the ancient world? Share your thoughts in the comments below. Delhi, India. Hidden beside the ruins of Mehrauli, Zafar Mahal became the final palace of the collapsing Mughal Empire, and one of the strangest engineering mysteries ever left behind by a dying civilization. Built in the 19th century when Mughal power had already nearly vanished, the structure still contains materials, cooling systems, and load balancing techniques that continue to puzzle modern engineers today. The palace was first documented in detail during British surveys following the Indian Rebellion of 1857. Archaeologists later noticed something unusual. Despite pollution, monsoon erosion, earthquakes, and nearly 2 centuries of neglect, large portions of the structure remained remarkably stable. Some interior surfaces still preserved smooth plaster layers. Several vaulted sections showed minimal structural deformation. The deeper researchers examined the palace, the more difficult it became to explain how such advanced construction methods survived inside an empire that was supposedly collapsing economically and politically. Zafar Mahal was commissioned under Akbar Shah II and later expanded by Bahadur Shah Zafar, the final Mughal emperor. By this point, the Mughal Empire had already lost most of its territory, military strength, and financial control. British East India Company influence dominated northern India, and historical records describe severe reductions in royal revenue. That is what makes the palace so mysterious. Civilizations in decline normally lose architectural complexity. The late Western Roman Empire produced simpler structures than earlier Roman engineering. The final Maya cities reduced monument scale as resources disappeared. Yet Zafar Mahal appears to show the opposite pattern. Even during political collapse, Mughal builders still demonstrated highly refined knowledge of heat control, structural geometry, and material chemistry. The main entrance, known as the Hathi Gate, was designed large enough for decorated war elephants to pass through. The gate's massive arch distributes compressive forces with extraordinary efficiency. Modern structural analysis of similar Mughal arches has shown that their curvature minimizes stress concentration while maximizing load transfer into thick supporting walls. Some engineers compare the force distribution to principles later formalized in 19th century European bridge engineering. The mystery is not simply that the structure survived. The mystery is why such advanced construction knowledge still existed during the empire's final years. The greatest mystery surrounding Zafar Mahal is hidden inside its walls. Researchers studying Mughal architecture discovered that many structures used lime-based mortar mixtures far more sophisticated than ordinary historical cement. Samples taken from Mughal sites across northern India revealed combinations of slaked lime, crushed brick dust, plant extracts, molasses, organic fibres and natural resins. In some cases, proteins from pulses or fermented materials may also have been included. What shocked researchers was the microscopic behaviour of the material. Under scanning electron microscopy, some historical lime mortars show crystalline regrowth inside tiny fractures. When moisture enters small cracks, chemical reactions can trigger the formation of new calcium carbonate crystals that partially seal the damaged area over time. This process resembles what modern engineers now call self-healing concrete. Today, self-healing concrete is considered advanced experimental technology. Modern versions often rely on bacteria, capsules of limestone-producing chemicals, or engineered microstructures. Yet Mughal builders may have achieved a primitive version centuries earlier using only natural materials. Some historical Indian mortars demonstrate compressive strengths exceeding 5 megapascals, even after hundreds of years of environmental exposure. More importantly, lime mortars often survive thermal expansion better than rigid Portland cement, because they remain slightly flexible and breathable. In climates like Delhi, where summer temperatures can exceed 45 degrees Celsius, while winters may fall below 7 degrees Celsius, that flexibility becomes extremely important. This may explain why some colonial-era repairs using modern cement deteriorated faster than the original Mughal sections. The question is deeply unsettling. How did builders without modern chemistry develop a material system that modern conservation engineers still struggle to replicate accurately? Even more mysterious is the disappearance of the formula itself. Unlike Roman concrete, which left partial written descriptions from Vitruvius and other authors, many Mughal mortar recipes were transmitted orally through guilds of craftsmen. When the Mughal court collapsed after 1857, entire networks of artisans disappeared. Knowledge accumulated over centuries may have vanished within a single generation. Modern laboratories can identify ingredients, but reproducing the exact behaviour of the mortar remains difficult because the process depended not only on materials, but also on timing, humidity, mixing techniques, curing conditions, and regional craftsmanship traditions that were never fully recorded. In some ways, Zafar Mahal represents a lost technological language. Another major mystery is the palace's thermal design. Delhi experiences brutal seasonal extremes. Summer surface temperatures can push stone and brick structures above 60 degrees Celsius under direct sunlight. Yet parts of Zafar Mahal were designed to remain significantly cooler without any mechanical systems. The palace used several passive cooling strategies simultaneously. Thick masonry walls, shaded corridors, controlled airflow channels, internal courtyards, reflective surfaces, and nearby water features. Modern studies of Indo-Islamic architecture show that enclosed courtyards can generate pressure differentials that naturally pull cooler air through interior passages. Thick lime-plastered walls also slow thermal transfer, reducing indoor heat spikes during the hottest hours of the day. Some Mughal structures demonstrate indoor temperatures between 5 and 8 degrees Celsius, cooler than external conditions purely through passive design. What makes this remarkable is that formal thermodynamics would not emerge scientifically until centuries later. Yet Mughal architects appear to have mastered practical climate engineering through observation and accumulated experimentation. Modern sustainable architecture increasingly studies similar techniques because contemporary glass and steel buildings often consume enormous energy for air conditioning. Ironically, ancient structures like Zafar Mahal sometimes function more efficiently in extreme climates than modern urban buildings. Several vaulted sections of Zafar Mahal also display unusual acoustic behaviour. Whispers can travel unexpectedly across certain chambers while echoes disappear in others. Similar effects appear in medieval mosques, Byzantine churches and Persian domes. But the acoustic precision of some Mughal spaces suggests deliberate experimentation, rather than coincidence. Curved surfaces can focus sound waves towards specific interior points, while staggered wall textures scatter echoes and reduce distortion. Modern concert halls use advanced mathematical modelling to achieve similar acoustic balancing. Yet, builders at Zafar Mahal accomplish this using geometry, plaster curvature and intuition alone. Some researchers believe Mughal architects inherited centuries of accumulated Persian and Central Asian architectural knowledge, stretching back through Timurid engineering traditions. Others argue the builders developed highly sophisticated empirical methods after generations of experimentation with the domes and vaults. Either way, much of that practical knowledge is now gone. Do you think ancient civilizations truly lost technologies more advanced than we realize? Or are places like Zafar Mahal simply revealing how much historical knowledge has already disappeared over time? Share your thoughts in the comments below. The Ouriz Mountains of northeastern Algeria conceal one of the strangest engineering mysteries of the ancient world. Inside Batna Province, an ancient city vanished beneath desert sand for centuries before archaeologists uncovered something almost impossible for its time: a near-perfect urban grid built at the edge of the Sahara. Roads intersected with mathematical precision. Underground drainage still functioned after nearly 2,000 years, and massive stone structures survived brutal temperature swings capable of destroying modern concrete within decades. The deeper researchers studied the ruins of Timgad and the surrounding settlements, the more North Africa began to resemble not a distant Roman frontier, but a lost laboratory of ancient engineering. Timgad was founded around 100 AD under Emperor Trajan, but after centuries of abandonment, wind and sand slowly buried much of the city beneath the Sahara's edge. Major excavations began during the late 19th century when French archaeologists uncovered streets, theatres, baths, drainage systems and stone roads preserved with astonishing clarity. Nearby ruins, including Lambesis, reveal that Batna Province once contained one of the most advanced infrastructure networks in Roman Africa, built in terrain that should have made large-scale urban survival extremely difficult. The greatest mystery inside Batna Province is not simply that Timgad existed, but how accurately it was designed. From above, the city resembles a modern blueprint more than an ancient settlement. Its streets form a remarkably organised orthogonal grid, stretching across difficult terrain near the desert edge, while the Cardo Maximus and Decumanus Maximus intersect at almost exact right angles. Even today, many ancient cities contain visible distortions caused by erosion, terrain irregularities, or inaccurate surveying, yet Timgad displays surprisingly little deviation despite being planned nearly 2,000 years ago. What makes this difficult to explain is the technological reality of the Roman world. Engineers at the time supposedly relied on ropes, wooden rods, primitive levelling tools and manual observation, yet the city demonstrates spatial precision comparable to principles still used in modern civil engineering. Archaeologists studying Roman surveying methods discovered that sections of Timgad maintain minimal angular error across long distances. Preserving such alignment over hundreds of meters without laser levelling or optical instruments would have required extraordinary coordination, because even small cumulative mistakes could gradually distort the entire urban grid. The mystery becomes even more disturbing underground. Beneath the streets lies a drainage and sewage network engineered with extremely subtle gradients. Modern hydraulic systems depend heavily on precise slope calculation, because channels that are too steep create erosion, while channels that are too shallow cause stagnation and waste build-up. Several underground conduits at Timgad appear to maintain gradients surprisingly close to those used in efficient gravity-fed systems today. This becomes astonishing when compared with modern infrastructure failures where small drainage miscalculations can flood entire urban districts within years. Yet parts of Timgad's underground network remain recognizable after nearly 20 centuries of desert erosion, seismic activity, and violent thermal expansion. Researchers also noticed that many streets appear oriented to optimize airflow and reduce heat accumulation. This matters because Batna Province experiences severe temperature variation, with summer temperatures exceeding 40 degrees Celsius, while nights in elevated desert terrain can become dramatically colder. In environments like this, urban orientation directly affects long-term survival. Some historians now believe Roman North Africa may have incorporated environmental knowledge from Berber populations familiar with desert adaptation centuries before Roman expansion. Ancient texts barely document these exchanges, leaving major gaps in understanding how climatic engineering became integrated into urban planning. The city's preservation itself created another mystery. Unlike Pompeii, which was rapidly sealed beneath volcanic ash, Timgad disappeared gradually beneath layers of sand over centuries. Ironically, the desert may have protected it. Sand-insulated pavements, walls, and underground systems from moisture fluctuation, oxidation, and human destruction. Archaeologists uncovered sectors where wheel marks remained visible in ancient stone streets. The result feels unnervingly modern. Timgad does not resemble the chaotic organic growth typical of many ancient cities. It resembles a carefully engineered machine. Not far from Timgad stood Lambesis, headquarters of the Legio III Augusta. At first glance it appears to be another Roman military fortress, but deeper analysis revealed infrastructure far more advanced than expected for a semi-arid mountain environment. The fortress operated in terrain where sustaining thousands of soldiers should have been extraordinarily difficult, yet the site contained baths, workshops, sanitation systems, roads, storage facilities, and stable access to water. Maintaining such a complex required massive logistical organization. Estimates suggest a Roman legion could consume hundreds of thousands of liters of water every week when accounting for drinking, bathing, cooking, animals, and industrial activity. Supplying that amount in harsh desert terrain without pumps or mechanized transport would have demanded exceptional hydraulic planning. The engineering mystery grows larger when examining the construction itself. Several stone blocks transported into the region weighed multiple tons, yet the surrounding terrain contains no major river systems capable of simplifying transport. Moving such material through mountainous landscapes without cranes, engines, or steel machinery remains controversial even among modern reconstruction engineers. Roman records mention rollers, pulleys, sledges, and manpower, but many researchers argue these explanations fail to fully account for the efficiency and scale visible across North African infrastructure projects. Some historians suspect forgotten regional transport methods may have been adopted from indigenous populations experienced in mountain logistics, while others believe Roman engineering capabilities were simply far more advanced than surviving texts suggest. Either explanation creates the same uncomfortable possibility. The ancient technological world may have been significantly more sophisticated than traditional history admits. Water should have been the greatest limitation for every settlement inside Batna Province, yet ancient builders developed systems that appear specifically optimized for desert survival. Multiple aqueducts and underground channels were constructed below surface level to reduce evaporation from direct sunlight, while thick masonry insulated flowing water from extreme heat exposure. Certain hydraulic mortars used in the region show unusual resistance to cracking despite centuries of thermal cycling. Scientifically, this matters because desert environments destroy materials rapidly. Daily expansion and contraction place enormous stress on both stone and mortar, and modern concrete exposed to harsh climates often develops major degradation within decades if poorly engineered. Yet some Roman-era materials in Batna Province survived nearly 20 centuries. Laboratory studies on Roman hydraulic concrete elsewhere in the Mediterranean revealed chemical reactions involving lime and volcanic ash capable of strengthening materials over time through mineral crystallization. Although North African mixtures differed from Italian marine concrete, some archaeologists believe regional formulas may have contained locally adapted mineral compositions. Modern science still struggles to reproduce completely. In practical terms, these systems functioned almost like passive climate control technology. Water remained cooler underground, thick masonry stabilized interior temperatures, and urban layouts improved airflow throughout the city. In some structures, the difference between exterior and interior temperatures may have significantly improved food preservation and human endurance during extreme heat. These were not simply architectural conveniences, they were environmental engineering systems designed to keep entire urban populations alive in one of the harshest climates connected to the Roman world. One of the greatest mysteries of Batna Province is the extraordinary durability of its ancient structures. The region faces intense UV radiation, desert winds, thermal shock, earthquakes, and long-term desertification, yet many ruins have survived for nearly 2,000 years. Some walls still preserve extremely tight stone joints, despite having no steel reinforcement or modern cement. This becomes even more remarkable when many modern concrete structures can suffer major deterioration within only a few decades in harsh environments. Modern engineers believe some ancient construction systems may have been better optimized for weight distribution, flexibility, and thermal expansion resistance. The deeper researchers investigate these ruins, the harder the comparison becomes to explain. Using only hand tools and simple labour, ancient civilizations somehow built structures capable of surviving extreme environmental conditions for nearly 2,000 years. Do you think the ancient world once possessed engineering knowledge that modern civilization partially lost over time? Share your thoughts and theories in the comments below. Chambers Pillar rises alone in the Red Desert of Central Australia, nearly 160 kilometres south of Alice Springs. Standing roughly 50 metres tall, this isolated sandstone column has survived in one of the harshest environments on Earth for tens of millions of years. But the deeper researchers studied the pillar and the ancient Aboriginal pathway surrounding it, the stranger the site became. Long before maps, roads, or compasses existed in Australia's interior, people were already navigating enormous desert distances with astonishing precision, using stars, songs, geological landmarks, and environmental memory systems that modern science still struggles to fully understand. The site entered Western records in 1860 when explorer John McDowell Stuart passed through the region during his attempt to cross Australia from south to north. Stuart named the formation after James Chambers, one of his financial supporters, yet Aboriginal communities had known the pillar for thousands of years as part of a much older network of ceremonial and navigational routes embedded into the landscape itself. What makes Chambers Pillar unusual is that the mystery is not hidden underground. The mystery is the landscape itself. Unlike Stonehenge or the pyramids, Chambers Pillar contains no giant architecture, no carved temple complex, and no massive engineered walls. Instead, the anomaly lies in how ancient humans transformed an empty desert into a functioning information system without writing, machines, or visible infrastructure. One of the greatest mysteries surrounding Chambers Pillar is the ancient navigation network connected to it. The Australian interior is brutally hostile. Summer ground temperatures can exceed 60 degrees Celsius, annual rainfall is extremely low, and many regions contain almost no permanent water sources. Modern travellers crossing these environments require GPS systems, satellite communication, and carefully calculated fuel supplies. Yet, Aboriginal groups crossed these deserts repeatedly for trade, ceremonies, and migration long before modern technology existed. Researchers studying Aboriginal songlines discovered that many routes were encoded into oral traditions that functioned almost like living maps. Specific verses corresponded to hills, waterholes, rock formations, and travel directions. In some cases, the rhythm and sequence of songs mirrored the physical geography of the route itself. A traveller who memorised the song could theoretically navigate hundreds of kilometres across featureless terrain. What makes this system extraordinary is its accuracy. Anthropologists have documented songline routes extending across massive sections of Australia, some connecting regions separated by more than 3,000 kilometres. In practical terms, this meant ancient travellers could maintain continent-scale navigation without written maps. Chambers Pillar appears to have functioned as one of these major desert markers. Rising dramatically above the surrounding plains, the formation is visible from great distances and would have acted like a natural beacon in an environment where even slight navigational errors could become fatal. Some researchers compare the system to a biological GPS network. Instead of satellites and digital coordinates, the system integrated astronomy, geology, memory, music, and environmental observation into a single navigational technology. The astronomical aspect of this knowledge is particularly difficult to explain away as simple folklore. Many Aboriginal groups possessed highly detailed observations of the night sky. Seasonal changes, animal migrations, weather patterns, and ceremonial calendars were linked to the positions of stars in the Milky Way. The Southern Cross constellation was often used for orientation, while the appearance of specific stars marked environmental changes critical for survival. Several researchers studying Indigenous Australian astronomy noticed that some songlines mirror celestial pathways. Certain routes on Earth correspond symbolically to patterns in the sky, creating what some anthropologists describe as a dual navigation system, one terrestrial and one astronomical. At Chambers Pillar, this becomes especially intriguing because of the pillar's visibility and isolation. In flat desert terrain, a vertical landmark can function as a precise observational reference point. Some researchers believe formations like Chambers Pillar may have been used to monitor star risings, seasonal solar positions, and long-distance directional alignment. Unlike sites such as Stonehenge, there's no massive engineered observatory here. But that may be exactly why the knowledge remained underestimated for so long. Aboriginal astronomical systems relied less on monumental construction and more on environmental integration. The landscape itself became the instrument. Another mystery involves the petroglyphs and markings found around the region. Archaeological surveys have identified engravings and traces of repeated ceremonial use near Chambers Pillar, though many symbols remain difficult to interpret conclusively. Some geometric patterns resemble directional markers, while others appear connected to ritual pathways or cosmological stories. The difficulty lies in separating symbolic meaning from functional purpose. Modern researchers are increasingly recognizing that many ancient societies encoded practical survival information into mythology, ceremony, and art. In Australia, this may have allowed essential environmental knowledge to survive across thousands of years without written records. Some markings near the pillar are also positioned in areas that appear surprisingly difficult to access. Considering the fragile nature of sandstone surfaces, researchers still debate how ancient people repeatedly reached elevated positions without causing major structural collapse or erosion. But the most scientifically puzzling aspect of Chambers Pillar is not human at all. It is the pillar itself. The formation consists primarily of sandstone deposited during the Carboniferous period, roughly 350 million years ago. Over immense stretches of geological time, erosion stripped away most surrounding material, leaving the pillar standing in isolation. On paper, this should not be particularly unusual. Erosion regularly creates mesas, buttes, and rock columns throughout desert environments. What makes Chambers Pillar difficult to fully explain is its improbable durability. Sandstone is generally considered far less resistant than igneous rocks like granite or basalt. It is vulnerable to thermal stress, wind abrasion, water penetration, and granular disintegration. Yet Chambers Pillar has remained standing despite millions of years of exposure to extreme desert conditions. Temperatures in central Australia can fluctuate dramatically between day and night, producing continuous expansion and contraction inside the rock. Wind-driven sand acts like natural sand-blasting equipment, slowly stripping away exposed surfaces grain by grain. During rare but intense rain events, water infiltrates fractures and accelerates weathering. Under such conditions, isolated sandstone structures should gradually weaken and collapse. Yet Chambers Pillar persists. Geologists believe several unusual factors may explain its survival. One theory involves differential cementation. Certain sections of the sandstone appear to contain stronger mineral bonding agents, possibly iron-rich compounds or silica cementation, making portions of the structure significantly harder than surrounding rock layers. Another possibility is aerodynamic erosion behaviour. The pillar's shape may unintentionally reduce destructive turbulence around critical, load-bearing zones. In other words, the structure may have evolved through erosion into a naturally stable geometry that slows its own destruction. Comparisons are often made to formations in Monument Valley in the United States, where isolated sandstone towers also survived long-term erosion. But Chambers Pillar exists under particularly severe thermal conditions, making its continued stability especially remarkable. Laser scanning studies of similar sandstone formations show that erosion does not occur evenly. Tiny differences in mineral density can dramatically alter survival times over millions of years. In some cases, a slightly harder internal layer can preserve an entire structure while surrounding landscapes disappear completely. Still, no geological model perfectly explains why Chambers Pillar remained so visually dominant while neighbouring formations eroded into near-flat desert. This has led some researchers to describe the pillar as a geological survivor anomaly. The mystery becomes even more compelling when combined with Aboriginal environmental knowledge. Ancient communities not only recognised the importance of Chambers Pillar, but integrated it into survival systems that lasted thousands of years without industrial technology. Modern desert survival relies heavily on GPS, satellite systems, engines, and digital maps. Yet Aboriginal Australians survived using observational intelligence alone. They tracked wind changes, memorised groundwater signs, understood seasonal star movements, and used geological formations as environmental data systems. Some anthropologists describe this as a form of ecological engineering, not through machines, but through cognitive adaptation. This challenges a major assumption of modern civilization, that advanced technology must always leave behind visible infrastructure. At Chambers Pillar, the technology may have existed almost entirely inside human memory. The deeper scientists investigate these ancient systems, the harder they become to dismiss as primitive. Unlike many ancient civilizations whose knowledge vanished with their monuments, this system survived for thousands of years through stories, songs, and the landscape itself. Rayan Castle rises from the deserts of southeastern Iran like the remains of a civilization that understood engineering far better than history is comfortable admitting. Located near the slopes of Mount Heza in Kerkenez Province, This enormous fortified city was built almost entirely from mud brick, clay, straw and compressed earth. Yet despite standing in one of the harshest environments in the Middle East, near active seismic zones and exposed to centuries of desert erosion, major sections of the fortress survived for nearly 1,000 years. What makes Rayan disturbing to archaeologists is not simply its age. It is the growing realization that many of its engineering solutions resemble principles modern architects only began systematically studying in recent centuries. The ancient citadel was rediscovered and formally documented during archaeological surveys in the 19th and early 20th centuries, after much of the surrounding region declined and populations shifted elsewhere. At first glance, researchers believed Rayan was simply another decaying desert fortress similar to countless abandoned settlements across Iran. But detailed structural analysis revealed something unexpected. The city was not randomly assembled. It had been engineered with astonishing environmental precision. Rayan covers roughly 22,000 square meters and contains residential districts, military quarters, workshops, markets, stables, defensive towers, and a heavily fortified governor's sector. The city functioned like a self-contained machine designed to survive heat, drought, invasion, and time itself. Its walls, in some places over 10 meters high, were constructed using layered adobe techniques that should not have endured centuries of seismic activity. Yet many sections remained standing long enough for engineers to study them in detail. One of the first mysteries surrounding Rayan involves earthquake resistance. Iran sits on multiple active fault systems and experiences frequent destructive earthquakes. Modern reinforced concrete buildings often collapse under severe seismic stress, yet Rayan's ancient mud brick structures displayed unusual resilience. Unlike rigid concrete, adobe possesses a degree of flexibility. During earthquakes, highly rigid materials transfer force violently through the structure, often causing catastrophic failure. But Rayan's thick earthen walls appear to absorb and dissipate energy more gradually. Researchers comparing ancient Persian adobe architecture with modern seismic engineering discovered that the walls were rarely uniform. Some sections taper subtly upward, reducing stress loads higher in the structure. Curved arches and domed ceilings distributed force away from weak corners, while narrow corridors prevented large, unsupported spans from collapsing inward. These are principles now central to earthquake-resistant design. The comparison becomes even stranger when examining nearby Bam Citadel, another massive Iranian adobe fortress. In 2003, the Bam earthquake devastated large portions of the city, killing more than 26,000 people. Yet structural surveys afterward showed that certain older construction methods actually resisted seismic collapse better than some later modifications added during modern restoration attempts. This raised uncomfortable questions among engineers. Were ancient Persian builders using empirical knowledge about seismic stability that modern restorations accidentally weakened? Another mystery emerges from Rayan's thermal engineering. Desert climates create brutal environmental extremes. Summer temperatures in the region can exceed 40 degrees Celsius during the day before dropping dramatically at night. Maintaining stable indoor temperatures without electricity should have been nearly impossible. Yet measurements inside surviving adobe chambers showed that temperatures changed far more slowly than outside conditions. The explanation lies partly in thermal mass. Thick mud brick walls absorb heat slowly during the day and release it gradually at night. Some walls inside Rayan exceed 1 meter in thickness, creating natural thermal inertia. But the real sophistication appears in the city's airflow design. Wind catchers and elevated ventilation shafts redirected desert winds downward into living spaces, cooling interiors through pressure differences and passive airflow circulation. Modern climate engineers studying traditional Persian architecture have compared these systems to primitive air conditioning units. Some passive cooling structures in Iran can reduce interior temperatures by more than 15 degrees Celsius without consuming energy. What shocks researchers is that these systems were optimized centuries before modern thermodynamics formally existed as a scientific discipline. The city's water system presents another engineering mystery. Rayan existed in an environment where annual rainfall was extremely limited, yet the settlement supported permanent populations, animals, workshops, and agriculture. Archaeologists believe the fortress relied heavily on qanats, underground water channels developed in ancient Persia thousands of years ago. Qanats are among the most astonishing hydraulic systems ever created. Workers dug long underground tunnels with gradients so precise that water flowed naturally across vast distances without pumps. Some qanat systems stretched for dozens of kilometers beneath desert terrain. Even a minor error in slope could stop water movement entirely or flood the tunnel. Modern civil engineers studying surviving qanats found gradient variations measured in mere centimeters across enormous distances. Accomplishing this without laser surveying equipment or satellite mapping remains deeply difficult to explain. In some regions of Iran, qanat systems continued operating for over 2,000 years. The Persian underground hydraulic network was so effective that UNESCO considers it one of humanity's greatest engineering achievements. But perhaps the most disturbing mystery surrounding Rayan Castle involves the durability of its ancient mud brick materials. Adobe should not survive like this. Ordinary mud structures deteriorate rapidly under moisture, temperature fluctuation, erosion, and vibration. Modern unstabilized mud brick often begins degrading within decades if poorly maintained. Yet Rayan survived centuries of desert winds, seasonal flooding, thermal expansion, and earthquakes. Material scientists studying ancient Persian adobe discovered that these bricks were far more sophisticated than simple dried mud. The composition varied depending on structural purpose. Some samples contain carefully balanced mixtures of clay, sand, straw fibers, lime traces, and organic binding materials. Straw acted similarly to fiber reinforcement in modern composite materials, helping distribute stress and reduce cracking. The density of the adobe layers also appears highly controlled. Builders compacted materials in stages, allowing moisture content to stabilize gradually before additional layers were added. This reduced internal weaknesses caused by uneven drying. Certain surfaces may also have received mineral coatings that increased resistance against water penetration and erosion. Comparisons with modern concrete create an unsettling perspective. Reinforced concrete structures today often require major repair after only 50 to 100 years, especially in harsh climates. Steel reinforcement corrodes, concrete fractures and thermal stress weakens the material over time. Yet parts of Rayan endured for nearly a millennium using earth, straw, and techniques developed without industrial machinery. This has forced some researchers to reconsider assumptions about ancient technological primitiveness. Ancient Persian builders may not have possessed modern chemistry equations, but they understood materials experimentally at an extraordinary level. Their knowledge was accumulated through centuries of observation, failure, climate adaptation, and structural refinement. Rayan's urban design adds another layer to the mystery. The city was engineered defensively with remarkable sophistication. Attackers entering the fortress faced twisting corridors, restricted sightlines, layered gates, elevated firing positions, and maze-like movement patterns designed to fragment enemy formations. Military historians compare aspects of the layout to later defensive concepts found in medieval fortifications across Asia and Europe. Even the positioning of workshops and stables reflected strategic logic. Essential resources were protected deep within the fortress, while outer sectors absorbed initial attacks. The city functioned less like a collection of buildings and more like an integrated survival system. Do you think ancient civilizations understood sustainable engineering better than we do today? Share your thoughts and theories in the comments below. Al-Baleed Archaeological Park stands on the southern coast of Oman, where desert cliffs meet the Arabian Sea. Today the ruins look silent and fragile, but nearly 1,000 years ago this was one of the richest ports on Earth. Ships crossed thousands of kilometers of dangerous ocean to reach it for a substance once valued almost like gold: frankincense. What archaeologists discovered beneath the sand was not just a lost trading city, but evidence of engineering systems, climate adaptation, and preservation technologies that still remain partially unexplained. The ruins of Al-Baleed were systematically investigated during the 20th century after scholars connected the site to medieval Arab records describing the prosperous port of Zafar. Excavations uncovered fortified walls, mosques, storage complexes, harbour structures, drainage systems, and imported ceramics from China, Persia, East Africa, and India. Radiocarbon analysis and ceramic studies suggest the city flourished between the 8th and 16th centuries CE during the peak of the Indian Ocean trade network. But the deeper archaeologists excavated, the stranger the site became. This is the greatest technological mystery surrounding Al-Baleed. Frankincense is not an ordinary trade good. It is a resin harvested from boswellia trees growing in harsh environments across southern Oman and parts of Yemen. In the ancient world, it was burned in temples, used in embalming rituals, medicine, perfume production, and elite ceremonies. Roman historians described Arabian frankincense as one of the most valuable substances entering the Mediterranean world. But frankincense presents a major problem. The resin rapidly degrades when exposed to excessive humidity, unstable temperatures, salt air, or microbial contamination. Long-distance maritime transport across the Arabian Sea should have damaged massive quantities of cargo. Yet historical records repeatedly describe Omani frankincense arriving in remarkably high condition, even after voyages lasting weeks or months. At Al-Baleed, archaeologists discovered evidence suggesting the city may have possessed advanced passive preservation systems far beyond what historians once assumed medieval Arabian ports could achieve. Some storage buildings contain unusually thick walls, narrow ventilation corridors, airflow-oriented layouts, and chambers positioned according to prevailing monsoon winds. Researchers noticed that certain warehouses appear designed to stabilize internal temperatures naturally, resembling principles seen in Persian wind catchers, Roman passive cooling systems, and even modern climate-responsive architecture. In some areas, wall thickness changes depending on exposure to sunlight and seasonal wind direction, suggesting the builders understood thermal transfer with surprising sophistication. Modern studies on traditional Arabian construction show that thick lime-plastered walls can reduce interior temperature fluctuations by several degrees Celsius. Combined with controlled airflow, this could have dramatically slowed resin degradation. The mystery becomes even more significant when considering scale. Historical estimates suggest tons of frankincense move through southern Arabia annually. Ancient Roman sources claimed the incense trade generated enormous state revenues, while Pliny the Elder described caravans protected almost like military operations. Al-Baleed may have functioned as one of the critical maritime gateways connecting this trade to India and East Africa. Yet archaeologists still do not fully understand how such enormous quantities were preserved consistently in a humid coastal environment. Some researchers suspect the use of mineral-based sealing compounds, organic antifungal coatings, specialized ceramic storage containers, or controlled airflow engineering now lost to history. The site increasingly resembles a forgotten industrial centre rather than a simple medieval port. One of the strangest aspects of Al-Baleed is that the city survived for centuries in an environment that should have been extremely destructive to urban infrastructure. The Dhofar coast experiences salt-heavy air, seasonal monsoon moisture, intense heat, and shifting groundwater conditions. Most coastal settlements exposed to these conditions suffer rapid structural decay. Salt penetrates stone and brick, expands during crystallization, and gradually destroys walls from within. Even modern concrete suffers heavily under such conditions. Yet parts of Al-Baleed remained structurally stable for hundreds of years. Archaeologists discovered drainage channels and water control systems, suggesting careful management of groundwater and seasonal flooding. Some foundations appear elevated or layered in ways that reduce salt intrusion. This has led to comparisons with Roman marine engineering, Nabatean water systems at Petra, and Persian Saruj waterproof mortar technologies. Certain surviving plaster fragments contain unusually durable lime mixtures that resisted erosion far longer than expected. Researchers believe local builders may have combined shell-derived lime, ash, and mineral aggregates to create materials adapted specifically for coastal humidity. The engineering logic behind the city appears highly specialized for climate survival. Al-Baleed became wealthy because it stood at the center of one of the most dangerous maritime trade systems of the ancient and medieval world. The Arabian Sea is heavily influenced by monsoon cycles. Winds reverse seasonally, currents shift dramatically, and storms can become catastrophic. Navigating these waters without advanced instruments should have been extraordinarily risky. Yet merchants operating from southern Oman maintained trade connections extending west toward East Africa, east toward India, and north toward the Persian Gulf. Excavations uncovered imported ceramics from China's Song and Ming periods, showing that Al-Baleed participated in trade networks spanning thousands of kilometers. The mystery is not simply that these voyages existed, the mystery is their consistency. To maintain profitable trade over centuries, navigators needed accurate understanding of monsoon timing, stellar navigation, ocean currents, seasonal humidity, and cargo preservation. Arab navigators later became famous for celestial navigation techniques using stars and angular measurements, but some historians believe this knowledge may have originated from much older maritime traditions developed in ports like Al-Baleed. This raises a larger question: how much ancient oceanographic knowledge has been lost? The architecture of Al-Baleed appears designed not for beauty alone, but survival. Many structures use compact street layouts, controlled airflow corridors, strategic wall orientation, and materials optimized for thermal regulation. This resembles techniques later seen across Islamic desert architecture. Some researchers argue that cities like Al-Baleed mastered passive cooling centuries before industrial ventilation existed. Certain building remains indicate an understanding of solar exposure, shadow management, heat absorption, and nighttime cooling cycles. In modern sustainability research, passive cooling systems inspired by Middle Eastern architecture can reduce indoor temperatures by 5 to 10 degrees Celsius without mechanical air conditioning. That makes Al-Baleed remarkable because its builders achieved environmental adaptation using only stone, lime, airflow, geometry, and local materials. No electricity, no machines, and no modern engineering software existed, yet the city functioned for centuries in one of the harshest coastal climates in Arabia. Perhaps the greatest unanswered question is why such a wealthy city disappeared. Historical evidence suggests Al-Baleed declined between the 15th and 16th centuries. Trade routes shifted, political instability increased, and some evidence points toward destructive conflict. But archaeology reveals a more complicated story. Certain areas show burning damage, others appear gradually abandoned, and some sections were buried unusually quickly by sand accumulation. Researchers proposed multiple explanations, including regional warfare, economic collapse, climate change, disease, or changing maritime routes after the rise of Portuguese naval power. Yet no single theory explains everything. A city that once controlled one of the world's most valuable trade commodities simply faded into silence. And beneath the ruins remained signs of engineering knowledge that still has not been fully reconstructed. Do you think Al-Baleed was simply an ancient trading city, or the remains of a forgotten technological civilization that understood climate preservation and maritime engineering far better than we realize today? Share your thoughts in the comments below. In central Anatolia, nearly 100 kilometers southwest of modern Ankara, a massive artificial hill rises above the dry plains of Turkey. Beneath it lies Gordian, the ancient capital of Phrygia and the legendary city of King Midas. But the real mystery of Gordian is not gold, it is engineering. Hidden under layers of burned cities, collapsed walls, and sealed burial mounds are structures that have survived for almost 3,000 years, with a level of material preservation and architectural stability that still confuses archaeologists today. Although travellers had noticed the enormous mound for centuries, systematic excavation only began in the 1950s under the University of Pennsylvania Museum led by Rodney Young. What archaeologists uncovered was shocking. Gordian was not a single city buried in time. It was a layered megastructure of civilizations stacked on top of one another, with some occupation phases dating back to roughly 2500 BCE. The central citadel mound alone rose over 50 meters high and covered nearly 13 hectares, making it one of the largest artificial settlement mounds in the ancient Near East. The deeper researchers excavated, the stranger the sight became. Entire districts appeared carefully rebuilt after catastrophic destruction events. Massive wooden chambers remained partially intact after nearly 3 millennia underground. Some walls still showed evidence of advanced reinforcement methods. Instead of resembling a primitive Iron Age settlement, Gordian increasingly looked like a city engineered to survive disaster. Most ancient cities expanded naturally over time. Gordian appears different. Archaeologists discovered evidence suggesting the mound itself was deliberately stabilized, using alternating layers of compacted earth, stone debris, clay, and construction fill. These layers likely distributed weight and reduced structural instability across the settlement. This matters because central Anatolia sits within a tectonically active region. Modern engineers use layered soil stabilization techniques to reduce vibration and settlement damage, especially in earthquake-prone areas. Yet evidence from Gordian suggests builders may have understood similar structural principles almost 3,000 years ago. The city's fortification walls also raise questions. Some defensive walls exceeded 8 meters in height and used carefully fitted limestone blocks combined with timber reinforcements embedded within the masonry. Similar hybrid systems later appeared in Greek and Roman seismic construction, but Gordian predates many of those examples by centuries. Researchers found signs that timber was intentionally inserted into walls not simply for support, but to absorb stress and distribute movement. In modern structural engineering, flexible reinforcement is essential for resisting vibration and thermal expansion. Whether the Phrygians understood the physics behind it remains unknown, but the practical result was remarkably effective. The greatest mystery of Gordian lies inside Tumulus MM, a colossal burial mound approximately 53 meters high and over 300 meters in diameter. It is one of the largest burial mounds ever discovered in Anatolia and is widely associated with the family of King Midas, likely his father Gordius. Inside the mound, archaeologists uncovered something almost impossible: an enormous wooden burial chamber still standing after nearly 2,700 years. Wood is one of the least durable ancient building materials. Under normal conditions, moisture, bacteria, fungi and insects destroy timber rapidly. Yet many beams inside Tumulus MM remained astonishingly well preserved. Some retained tool marks, others still held their structural alignment despite supporting immense pressure from thousands of tons of earth above them. The chamber itself measured roughly 5 by 6 meters and was constructed using massive cedar and juniper beams precisely interlocked without relying heavily on metal fasteners. Some timbers exceeded 25 centimeters in thickness. The engineering precision was extraordinary. Every beam distributed weight in a way that prevented collapse even as the mound compressed over centuries. What confuses researchers is the preservation environment. Scientists believe several factors contributed: low oxygen levels, stable internal humidity, clay ceiling layers, and compression from the mound itself. But none fully explain the chamber's condition. Comparable wooden tombs from similar periods across the Near East usually collapsed or decomposed long ago. Even more mysterious is the possibility that the builders intentionally engineered a controlled microclimate inside the mound. Some specialists argue the Phrygians may have understood passive humidity regulation through layered soil density and air restriction. Certain clay mixtures appear to have acted almost like natural insulation barriers. The burial chamber essentially functioned as a sealed preservation capsule. Modern comparisons make the mystery even more striking. Many medieval wooden structures from only 700–900 years ago have deteriorated far worse than the Tumulus MM chamber. Some researchers compare the preservation conditions to the tomb of Xinjui in China, or the frozen Scythian tombs of Siberia, yet Gordian achieved remarkable preservation without ice, chemical embalming or permafrost. The burial feast discovered inside deepened the mystery further. Large bronze cauldrons, iron tools, wooden furniture, woven textiles, and residues of fermented beverages survived in extraordinary condition. Chemical analysis revealed evidence of a mixed alcoholic drink containing barley beer, grape wine, and honey mead. Some researchers recreated the recipe in modern laboratories, showing the Phrygians possessed advanced fermentation practices centuries before many later European brewing traditions. But perhaps the strangest detail is psychological rather than physical. The tomb does not feel improvised. Every structural element suggests planning, testing, and long-term design. Whoever built Tumulus MM understood load distribution, environmental control, timber selection, and burial sealing with a sophistication that feels unexpectedly modern for the Iron Age. At some point around 800 BCE, Gordian suffered a catastrophic fire. Excavations revealed thick destruction layers filled with ash, collapsed roofs, and carbonized debris. Temperatures during the blaze may have exceeded 800 degrees Celsius in some sectors. In most ancient cities, fires of that scale caused permanent decline, but Gordian rapidly rebuilt itself. The reconstruction phase shows evidence of improved urban planning. Streets became more organized, walls were thicker, storage systems expanded. Some buildings incorporated alternating timber and stone construction patterns that reduced cracking during thermal stress and seismic vibration. This is one of the site's biggest mysteries. The rebuilding process suggests the inhabitants learned from disaster and deliberately redesigned the city for resilience. Modern disaster engineering follows similar principles after earthquakes and urban fires: flexible reinforcement, compartmentalized construction, distributed load-bearing systems, and controlled rebuilding layouts. Gordian appears to have implemented versions of these ideas nearly 3 millennia ago. Another unexplained feature of Gordian involves its storage infrastructure. Archaeologists uncovered large subterranean grain storage pits capable of preserving massive food reserves through harsh seasonal cycles. Central Anatolia experiences extreme environmental variation. Summer temperatures can exceed 35 degrees Celsius, while winters regularly drop below freezing. Yet the storage systems maintained relatively stable internal conditions. Researchers believe the pits exploited thermal inertia underground, minimizing temperature fluctuations naturally. Some also show evidence of carefully designed ventilation pathways that reduced moisture accumulation and prevented mold growth. The scale is equally important. Estimates suggest Gordian stored enough grain to support large populations or military forces for extended periods. This indicates not merely agricultural success, but logistical planning on a state level. Compared to many neighbouring Iron Age settlements, Gordian's storage network appears unusually centralised and technically organised. One of the most fascinating structures at Gordian is the so-called Mosaic Building. Its floor contains one of the oldest known pebble mosaic surfaces in the ancient world. At first glance, the patterns appear decorative, but detailed measurements revealed extraordinary geometric consistency. Thousands of pebbles were arranged into repeating angular motifs, with highly controlled symmetry across a large surface area. Creating such precision without modern measuring instruments would have been extremely difficult. Minor angular errors compound rapidly over distance, especially in large geometric layouts. Yet the builders maintained remarkable proportional accuracy. Some archaeologists believe this suggests advanced practical geometry knowledge among Phrygian craftsmen. Similar mathematical sophistication later became famous in classical Greek architecture, but Gordian predates many of those achievements. Do you think the engineers of ancient Gordian truly understood advanced construction techniques far beyond their time, or are we still missing part of the story? Share your thoughts in the comments below. Dalverzin Tepe lies in southern Uzbekistan near the Afghan border, hidden beneath layers of desert soil for nearly 2,000 years. What archaeologists uncovered there was not just another Silk Road settlement, but a city whose engineering, metallurgy and wealth appear far more advanced than historians once believed possible for ancient Central Asia. The site was first identified in the 1930s and heavily excavated by Soviet archaeologists beginning in the 1960s. Beneath Clap's mud brick walls, researchers discovered a fortified Kushan-era city covering more than 47 hectares, filled with workshops, temples, defensive walls, hydraulic systems, and one of the richest ancient gold hoards ever found in the region. But the deeper the excavations went, the stranger Dalverzin Tepe became. Yet the greatest mystery of Dalverzin Tepe emerged from a sealed chamber discovered during excavations in 1972. Inside was an enormous Kushan gold treasure containing necklaces, belts, medallions, coins, rings, and ceremonial ornaments, weighing more than 36 kilograms in total. The discovery shocked Soviet researchers not simply because of its value, but because of the extraordinary manufacturing precision visible under magnification. Many pieces displayed granulation work so refined that individual gold spheres measured less than a millimeter in diameter. Even modern jewelers consider this technique extremely difficult because it requires heating tiny gold particles to the exact threshold where they fuse onto a surface without melting completely. A slight temperature error destroys the entire design. Ancient craftsmen at Dalverzin Tepe somehow achieved this repeatedly using furnaces that supposedly lacked modern thermal regulation. Metallurgical studies later suggested that Kushan goldsmiths may have used chemical bonding compounds containing copper salts or organic fluxes to locally lower surface melting temperatures. This would have allowed microscopic fusion at precise points while preserving the rest of the object. Similar theories have been proposed for Etruscan jewellery in Italy, but Dalverzin Tepe demonstrates comparable sophistication thousands of kilometres away in what many once considered a peripheral civilization. The purity of the gold itself created additional debate. Several artefacts contained extremely high gold concentrations with remarkably low contamination levels. Ancient refining normally leaves behind significant traces of silver, lead or copper impurities unless highly advanced separation methods are used. Some researchers speculate Kushan metallurgists may have mastered multi-stage cupellation or chemical purification techniques far earlier than previously assumed for the region. Microscopic surface analysis revealed polishing marks so fine that some specialists believe extremely hard abrasives may have been used during finishing. Quartz sand alone may not fully explain the smooth reflective surfaces found on certain ornaments. Similar polishing anomalies have appeared in Egyptian goldwork and some Roman luxury objects, but Dalverzin Tepe pushes this level of craftsmanship into the heart of ancient Central Asia. One of the first mysteries involved the city's survival itself. Dalverzin Tepe stood in a brutally arid environment where summer temperatures regularly exceed 40 degrees Celsius. Mud brick structures in climates like this normally erode rapidly through thermal expansion, wind abrasion, and salt crystallization. Yet many of the city's walls survived nearly intact for close to 2,000 years. Material analysis revealed that the Kushan builders mixed clay with finely processed organic fibers and mineral tempering agents, creating bricks with unusually high resistance to cracking. Some engineers compared the structural behaviour of these bricks to primitive composite materials, because the organic inclusions distributed stress throughout the wall instead of allowing fractures to spread freely. The city's layout also raises difficult questions. Excavations revealed carefully organised districts separated by defensive corridors, industrial zones, and ceremonial spaces. Streets appear aligned according to airflow patterns that may have helped cool the city naturally during extreme heat. Certain residential compounds contained narrow ventilation channels embedded within thick mud brick walls, functioning similarly to passive cooling systems later seen in Persian desert architecture. Some archaeologists believe Dalverzin Tepe may represent an early large-scale experiment in climatic urban engineering centuries before such techniques became widespread across Central Asia. The city also contained evidence of surprisingly large-scale industrial activity. Archaeologists uncovered metalworking areas, ceramic kilns, sculpture workshops, and jewellery production districts operating simultaneously inside the fortified city. Slag residues and furnace remains indicate continuous metallurgical production rather than occasional artisan activity. This suggests Dalverzin Tepe functioned not merely as a trading post, but as a major manufacturing centre connected to Silk Road supply systems. Isotopic analysis of materials found at the site suggests raw resources arrived from multiple distant regions. Certain gemstones likely originated from Badakhshan in present-day Afghanistan, while stylistic influences in metalwork connect the city to Hellenistic Greece, Persia, India, and nomadic steppe cultures simultaneously. Few ancient cities demonstrate such concentrated technological and artistic fusion across so many civilizations at once. This fusion becomes even stranger in the city's sculptures and religious imagery. Excavations uncovered Buddhist statues displaying clear Hellenistic anatomical proportions alongside Persian decorative motifs and Indian spiritual iconography. Some sculptural drapery techniques resemble Gandharan art from northern Pakistan, while facial structures echo Greco-Bactrian traditions established after Alexander the Great's campaigns centuries earlier. The precision of these sculptures suggests access to advanced geometric planning systems. Certain statues display body ratios approaching the mathematical proportional systems associated with classical Greek sculpture. Whether Kushan artists inherited these methods directly or developed hybrid local adaptations remains unclear, but the result was a visual language unlike almost anything else in the ancient world. Another unresolved mystery involves the city's pigments and wall paintings. Fragments recovered from temples and elite compounds retained visible reds, blues, and yellows despite nearly 2 millennia of burial and exposure to mineral-rich desert soils. Chemical studies identified stable mineral pigments combined with unusually durable binding agents. Some researchers suspect organic resins or protein-based stabilizers similar to cassine may have been used to improve adhesion and prevent fading. The durability of these pigments has drawn comparisons to Roman frescoes at Pompeii and Egyptian tomb paintings. Yet Dalverzin Tepe existed in a far harsher thermal environment. Temperatures in the region fluctuate dramatically between scorching daytime heat and cold desert nights, conditions that normally accelerate pigment separation and plaster cracking. Even the city's defensive walls remain difficult to explain fully. Massive fortifications surrounded Dalverzin Tepe, constructed atop terrain vulnerable to erosion and shifting soil density. Engineers studying the ruins observed layered foundation systems that distributed weight efficiently across unstable ground. Certain wall sections appear intentionally segmented to absorb thermal expansion without catastrophic cracking, an approach surprisingly similar to stress management principles used in some modern masonry designs. And then there is the final mystery, the city's disappearance. Despite its wealth, industrial capacity and strategic position, Dalverzin Tepe eventually declined and was abandoned. No single explanation fully accounts for the collapse. Some historians blame shifting trade routes. Others point to political instability within the Kushan Empire, regional invasions, or changing river systems that disrupted agriculture and transport. But the archaeological evidence suggests the decline may have happened faster than expected for a city of such importance. Industrial activity appears to have slowed abruptly in some sectors. Certain workshops were abandoned with tools still inside. Parts of the city show signs of hurried abandonment rather than gradual decay. Do you think Dalverzin Tepe was simply a forgotten Silk Road city, or evidence that an advanced technological centre once existed in ancient Central Asia far beyond what history currently admits? Share your thoughts in the comments below. Hassanlu Tepe sits near the southern edge of Lake Urmia in northwestern Iran, where archaeologists uncovered one of the most violently preserved ancient cities ever found. Around 800 BCE, the entire settlement was destroyed in a catastrophic fire so sudden that people died where they stood, leaving behind frozen moments of panic buried beneath collapsed mud brick and burning timber. Nearly 3,000 years later, Hassanlu still contains mysteries that modern archaeology and engineering cannot fully explain. The site was first excavated systematically in the 1950s by Robert H. Dyson Jr. from the University of Pennsylvania. Beneath multiple occupation layers, archaeologists uncovered a major Iron Age city destroyed in a single event. Entire rooms remained sealed under debris. Human skeletons were discovered trapped in stairways, alleyways, and collapsed halls. Unlike many ancient ruins slowly abandoned over centuries, Hassanlu looked as if time had stopped in one night. The destruction layer itself became one of the greatest archaeological time capsules of the ancient Near East. The deeper researchers studied Hassanlu, the stranger the site became. The fire that destroyed Hassanlu was not an ordinary urban fire. Evidence from burned timber, vitrified mud surfaces, and collapsed architecture suggests temperatures may have exceeded 800 degrees Celsius in some sections, comparable to temperatures used in primitive industrial firing processes. Mud brick structures normally disintegrate rapidly when exposed to centuries of moisture and freeze-thaw cycles, yet many Hassanlu walls survived in recognizable form for nearly 3 millennia. Archaeologists believe the destruction itself may have accidentally preserved the city, because the intense heat likely hardened portions of the mud brick in a process similar to low-temperature ceramic firing. This phenomenon has been compared to partially fired mud brick structures found at sites in Mesopotamia, but Hassanlu's preservation is unusually extensive. Some walls collapsed inward while still structurally semi-rigid, trapping entire rooms beneath sealed debris layers. Organic materials, including wooden beams and food remains, were preserved in carbonized form because oxygen levels rapidly dropped beneath the rubble. Researchers still debate how the fire spread so quickly through such a large settlement. Some believe attackers deliberately targeted roof supports and storage zones to create chain reaction collapses, while others suspect the architecture itself unintentionally amplified the destruction. Large, timber-reinforced mud brick buildings may have functioned like enormous furnaces once ignited. The most famous object ever discovered at Hassanlu is the Hassanlu Gold Bowl, found clutched by a man who died while apparently trying to escape the burning city. Weighing nearly 1 kilogram and made from high-purity gold, the bowl is covered with intricate mythological scenes hammered into the metal with astonishing precision. What makes the artifact extraordinary is not simply its beauty, but the technical sophistication required to manufacture it around the 9th century BCE. The bowl was likely produced using repousse and chasing techniques, where craftsmen hammered designs from the reverse side and refined details from the front. However, metallurgical analysis suggests an unusually advanced level of control over gold thickness and stress distribution across the surface. In many ancient repousse works, repeated hammering creates weak points, uneven surfaces, or microfractures, yet the Hassanlu bowl displays remarkably consistent structural integrity despite its dense relief imagery. Some sections contain extremely fine raised details only millimeters deep, requiring controlled force distribution across thin gold sheets without tearing the metal. Even modern restorers note how difficult it would be to reproduce the bowl accurately using reconstructed Iron Age tools alone. The symmetry of the imagery also raises questions, because several circular compositions maintain highly balanced spacing, despite being executed entirely by hand. Without modern calipers, precision grids, or optical measuring systems, maintaining proportional continuity around a curved golden surface would have required extraordinary planning. Comparisons with the Syrian and Eurasian metalwork from the same period show similarities in iconography, yet the Hassanlu bowl often appears technically more refined in depth transitions and compositional density. Some researchers believe the craftsmen may have inherited older metallurgical traditions now completely lost. Even more mysterious is the gold itself. Trace element analysis suggests the metal may have originated from multiple ore sources, implying long-distance trade networks or sophisticated recycling practices. At a time when transportation across the Zagros region was extremely difficult, Hassanlu somehow had access to elite materials and artisans capable of working them at near masterpiece level. To this day, archaeologists still cannot fully explain how craftsmen prevented deformation during deep repousse work, how they controlled heating and annealing cycles without modern temperature measurement, how they achieved such uniform thickness across large hammered sections, or how such advanced artistry emerged in what was supposedly a peripheral highland settlement rather than an imperial capital. The bowl feels less like an isolated artwork and more like surviving evidence of a technical tradition mostly erased from history. Hassanlu stood in a tectonically unstable region where earthquakes were common, Yet several major structures show evidence of engineering strategies that appear unusually resilient for the Iron Age. Many walls were constructed with thick mud brick exteriors reinforced internally by timber frameworks, a combination resembling anti-seismic techniques later seen in Persian and even some medieval Middle Eastern architecture. Wood absorbs and redistributes vibrational energy more flexibly than solid masonry alone. Some collapsed walls bent and folded instead of exploding outward into fragmentation. Structural engineers studying ancient earthquake damage patterns note that this behaviour suggests partial energy dissipation inside the wall cores. At other Near Eastern sites from the same era, pure mud brick construction often failed catastrophically during seismic activity, but Hassanlu's hybrid structural methods may have significantly improved survival rates during smaller tremors. The mystery is whether these builders truly understood seismic behaviour experimentally, or whether the design evolved accidentally through generations of reconstruction after repeated earthquakes. Either explanation implies a level of architectural adaptation more sophisticated than traditionally assumed for Iron Age settlements. Standard mud brick architecture deteriorates relatively quickly in regions exposed to seasonal moisture and winter freezing. Northwestern Iran experiences harsh winters, temperature variation, and periodic precipitation, conditions normally destructive to unfired earthen structures. Yet Hassanlu's destruction layer remained remarkably stable. Material analysis revealed unusually dense mud brick mixtures containing fine mineral inclusions, organic fibres, and carefully sorted clay compositions. Some samples exhibit compressive strengths noticeably higher than standard Near Eastern mud brick from comparable periods. Researchers suspect builders may have intentionally added volcanic ash, silica-rich sediments, or plant fibres to reduce cracking during drying. Similar stabilizing principles appear later in Persian Saruj mortar and Roman pozzolanic concrete, though Hassanlu predates many famous examples of advanced ancient composite materials. The consistency of the mixtures suggests standardized production methods rather than random local improvisation, implying skilled material specialists existed within the settlement. Hassanlu was not Babylon or Nineveh, yet the number of elite artifacts discovered there suggests access to wealth, trade, and skilled labour far beyond what archaeologists expected from a regional settlement. Imported materials, luxury goods, weapons, and complex storage systems indicate Hassanlu held a strategic position between Mesopotamia, Anatolia, and the Iranian plateau. Large storage rooms and administrative ceilings point to organised food management and bureaucratic control over trade and resources. What makes this difficult to explain is that Hassanlu thrived in a mountainous frontier region, surrounded by constant warfare between Assyria, Urartu, and local powers. Despite that instability, the city maintained a level of economic organisation and technical sophistication far beyond what its size would normally suggest. Who do you think truly destroyed Hassanlu? And how much ancient knowledge may have vanished in that single night of fire? Share your thoughts in the comments below. Almendres Cromlech stands silently across the hills near Evora, Portugal. But this was never just a circle of stones. Built nearly 7,000 years ago, long before most of Europe developed cities, writing, or metal tools, Almendres appears to function like a gigantic prehistoric sky map. More than 90 granite monoliths were arranged with such deliberate astronomical precision that researchers still debate whether Stone Age humans truly possessed the observational knowledge required to build it. The deeper archaeologists study the site, the less primitive its craters begin to look, Although local people had known about the stones for centuries, Almendres was formally identified by archaeologist Henrique Leonor Pinar in 1966, after the surrounding forest was partially cleared. What initially appeared to be scattered megaliths soon revealed a carefully organised structure dating back to roughly 6,000–4,000 BCE, making it older than both Stonehenge and many Egyptian pyramids. Radiocarbon studies, ceramic fragments and soil analysis confirmed that the complex evolved over multiple construction phases across centuries, possibly even millennia. The greatest mystery surrounding Almendres is not the stones themselves, but their orientation. Researchers discovered that several alignments inside the complex correspond closely with sunrise during the winter solstice, equinox light positions, lunar standstill cycles, and seasonal celestial movements visible over the Iberian horizon. Some stones appear positioned specifically to frame solar movement during precise days of the year, leading archaeologists to describe Almendres as one of the earliest known astronomical observatories in Europe. The problem is timing. Almendres was constructed during the Neolithic period, when human societies in Western Europe supposedly relied mostly on simple farming tools, primitive shelters, and oral traditions. Yet achieving this type of astronomical alignment would have required generations of uninterrupted observation. To understand the scale of the challenge, modern archaeoastronomers note that lunar standstill cycles repeat approximately every 18.6 years. Detecting those patterns without written records would demand long-term tracking over decades, possibly centuries. This immediately raises an uncomfortable question. How could a Stone Age society preserve observational accuracy across multiple generations without advanced mathematics or writing systems? The precision becomes even more difficult to dismiss when compared to other ancient astronomical sites. Newgrange aligns with winter solstice sunlight, Nabta Playa may track stellar movement, Chaco Culture National Historical Park contains solar and lunar alignments, and Karnak Stones demonstrates massive geometric organisation. But Almendres predates many of them. Some researchers believe the site functioned as a ceremonial calendar used to predict seasonal agricultural changes. Others argue the alignments are too numerous and too intentional to be purely ritualistic. A few even suggest Almendres may represent one of humanity's earliest attempts to create a physical model of the heavens on Earth. The stones of Almendres are not small decorative markers. Many weigh several tons and consist primarily of dense granite transported from surrounding regions. That creates a major engineering problem. Granite is one of the hardest natural stones available. Even modern quarrying requires powerful industrial cutting equipment. Yet Neolithic builders supposedly possessed only stone tools, wooden sledges, rope and human labour. No iron, no steel, no cranes. Possibly not even fully developed wheeled transport. Despite those limitations, the stones were not merely moved. They were shaped, positioned upright, and arranged according to astronomical orientation. This means the builders had to simultaneously solve transportation logistics, terrain navigation, weight distribution, structural stability, and celestial positioning. Experimental archaeology has shown that moving multi-ton stones with primitive technology is theoretically possible, but extremely slow and labour-intensive. Some reconstructions estimate that transporting a single large megalith over rough terrain could require hundreds of workers. Yet Almendres was built in phases over centuries with remarkable consistency. Even more puzzling is the placement geometry. The stones are arranged in elongated circular patterns rather than random clusters, suggesting deliberate surveying methods. Modern engineers studying prehistoric monuments often note that establishing large-scale geometric layouts without aerial perspective or advanced instruments is extraordinarily difficult. And yet, prehistoric builders across Europe repeatedly achieved it. Several stones at Almendres contain engraved markings, including concentric circles, curved lines, cup marks, and abstract geometric carvings. Some resemble symbols found at Gavrinus Cairn, Noth, and Val Camonica. The meaning remains unknown. Some archaeologists interpret them as fertility symbols or tribal markers, while others believe they could encode astronomical information connected to the movement of the sun and moon. One particularly debated theory proposes that certain carvings functioned as mnemonic systems, visual memory aids designed to preserve cyclical knowledge before the invention of writing. If true, Almendres may not simply represent architecture, it may represent data storage, not digital storage, but a prehistoric method of embedding observational knowledge directly into landscape and stone. Almendres has remained exposed to wind, rain, soil movement and temperature variation for nearly 7 millennia. Yet many stones remain standing. That survival suggests the builders understood foundational stability far better than expected for Neolithic societies. Some monoliths were buried deep into the soil at carefully calculated angles that reduce tipping forces over time, while others appear positioned to distribute weight naturally along terrain contours. Modern geological studies show that improperly placed standing stones gradually tilt due to soil creep and seasonal ground expansion. But many Almendres stones remain surprisingly stable despite thousands of years of environmental stress. This durability has drawn comparisons to Avebury, Stonehenge and Callanish stones. However, Almendres is significantly older than most of them, implying that advanced megalithic engineering traditions may have emerged in Europe far earlier than historians once believed. Some modern researchers suspect ancient megalithic sites were intentionally placed in areas with unusual geological properties. At Almendres, experimental acoustic tests suggest sound behaves differently depending on position within the stone arrangement. Certain locations produce stronger resonance and echo effects than nearby areas. Although the evidence remains inconclusive, similar theories have been explored at Stonehenge, Göbekli Tepe, and Hypogeum of Hal Saflieni. Some geologists also point out that megalithic monuments frequently appear near fault systems or magnetically unusual terrain. Whether prehistoric builders consciously understood these effects remains unknown. But it raises another unsettling possibility. Ancient humans may have possessed environmental knowledge that modern civilization has only partially rediscovered. Do you think Almendres Cromlech was simply a ritual site, or evidence that prehistoric civilizations understood the sky and engineering far better than we realize today? Share your thoughts in the comments below. Surrounded by the rugged landscape of southern Oman near Salalah, Ain Razat stood along one of the most important ancient frankincense trade corridors in Arabia. Archaeologists began closely studying the area during 20th century surveys of Dhofar's ancient water systems and caravan routes. What initially appeared to be a natural spring surrounded by ruins slowly revealed something far more unusual, evidence of a highly controlled hydraulic landscape operating in one of the harshest climates on Earth. Unlike massive monuments that dominate the horizon, Ain Razat hides its mystery inside engineering precision almost invisible to the naked eye. The greatest mystery surrounding Ain Razat is not the spring itself, but the sophisticated control of water flow around it. Dhofar receives seasonal monsoon moisture from the Indian Ocean during the Kharif season, yet for most of the year the surrounding environment remains semi-arid. Maintaining stable agriculture and caravan support systems in such conditions required extraordinary hydraulic understanding. Archaeological remains show carefully constructed channels, reservoirs, retaining walls, and distribution pathways positioned with remarkable accuracy across uneven limestone terrain. Even minor slope errors in ancient channels would have caused destructive erosion or stagnant water buildup. Modern hydraulic engineers know that maintaining efficient gravity-fed flow often requires gradients of less than 1%. At several ancient water systems across the ancient world, including Roman aqueducts, engineers maintained gradients averaging only a few centimetres per 100 metres. The famous Pont du Gard aqueduct in France, for example, drops roughly 17 metres across nearly 50 kilometres. What makes Ain Razat difficult to explain is that the local civilizations responsible for these systems left behind no obvious evidence of advanced surveying instruments comparable to Roman chorobates or later Islamic precision tools. Yet the channels appear deliberately calibrated to regulate seasonal flow fluctuations while minimizing water loss. Some researchers believe the builders may have used water level measuring methods, tensioned cords, astronomical orientation, or long-distance visual leveling techniques similar to those suspected in Persian Qanat engineering. However, no direct proof has ever been discovered. The engineering knowledge appears almost invisible, embedded directly into the landscape itself. Another major mystery involves the region's geology. Ain Razat sits within a limestone environment dominated by karst formations. Karst terrain is notoriously unstable for water storage because limestone naturally fractures, allowing water to disappear underground through cracks and subterranean channels. Yet several ancient reservoirs and collection areas near Ain Razat appear to have retained water far more efficiently than expected. This has led archaeologists to question whether ancient builders developed specialized waterproofing techniques now largely lost. In multiple ancient civilizations, advanced water sealing technologies existed far earlier than many historians once believed. Persian engineers created saruj, a waterproof mortar composed of clay, lime, ash, and organic materials. Roman concrete developed chemical reactions with seawater that allowed structures to survive for millennia. At Petra, the Nabateans engineered hidden cistern systems capable of storing enough water to support tens of thousands of people in desert conditions. Ain Razat may represent a southern Arabian version of this forgotten hydraulic science. Some excavation reports describe unusually compact sediment layers and artificial lining traces near portions of the ancient channels. If deliberate sealing methods were used here, it would suggest that the inhabitants understood hydrogeology at a surprisingly advanced practical level despite operating in a region often portrayed as technologically simple. One of the strangest aspects of Ain Razat is the environment itself. During the Kharif monsoon season, moisture from the Arabian Sea transforms Dhofar into one of the greenest parts of the Arabian Peninsula. Fog, mist, and low clouds dramatically reduce evaporation rates. Ancient structures at Ain Razat appear strategically positioned in areas with optimal humidity retention, cooler airflow, and reduced solar exposure. This has led some researchers to suspect that the site was intentionally designed to manipulate microclimate conditions. Modern environmental engineers use similar principles today. Temperature differentials, shade geometry, airflow corridors, and evaporative cooling systems are carefully calculated to preserve water and stabilize agriculture in dry climates. Some ancient societies achieved comparable effects without modern computation. Persian yakhchals preserved ice in deserts where summer temperatures exceeded 40 degrees Celsius. Nabatean architecture at Petra exploited canyon airflow to create cooler living environments. In Yemen, ancient terrace systems altered entire mountain ecosystems. At Ain Razat, the positioning of water channels and reservoirs may have created localized cooling zones capable of sustaining vegetation and caravan operations even during hotter months. If true, the site was not simply using nature, it was subtly engineering nature itself. The Dofa region was once the centre of the global frankincense trade, one of the most valuable industries of the ancient world. Frankincense resin was transported from southern Arabia to Egypt, Rome, Mesopotamia, Persia, India, and eventually China. In some Roman periods, frankincense rivaled precious metals in value due to its religious and medicinal importance. Ancient caravan networks crossing Arabia required carefully spaced water stations to survive. A single interruption in reliable water access could collapse entire trade routes. Ain Razat's hydraulic stability may explain why the site became strategically critical despite its isolated position. This raises a larger mystery. Was Ain Razat merely a local settlement surrounding a spring, or was it part of a much larger logistics network controlling trade movement across Arabia? Satellite mapping and archaeological surveys across Oman increasingly reveal interconnected caravan pathways, fortified stops, and water management systems extending across enormous distances. Some historians now believe ancient Arabian trade infrastructure was far more organised and technologically coordinated than previously assumed. The wealth generated through frankincense may have funded highly specialised engineering knowledge that disappeared after trade routes declined. If so, Ain Razat could represent only a surviving fragment of a much larger lost system. Perhaps the most difficult question is not how the system was built, but how it continued functioning for centuries. Ancient hydraulic systems require constant maintenance. Sediment accumulation, mineral deposits, biological growth, erosion, and seasonal flooding rapidly destroy unmanaged channels. Even modern concrete irrigation systems require continual repair. Yet archaeological evidence suggests water management around Ain Razat remained operational across multiple historical phases. This implies organised labour, technical oversight, and intergenerational transfer of engineering knowledge. Comparable systems elsewhere depended on highly specialised water experts. Persian Qanat networks required hereditary maintenance teams who understood underground tunnel behaviour. Roman aqueducts employed permanent engineering crews. In the Andes, Inca hydraulic terraces required constant coordinated upkeep, involving entire communities. At Ain Razat, no written manuals survive. No engineering diagrams remain. The knowledge system itself appears to have vanished almost completely, leaving behind only the physical evidence of its effectiveness. That disappearance creates one of the site's most unsettling mysteries. How much ancient technical knowledge has been entirely erased from history simply because it was transmitted orally rather than through durable records? Scattered around Ain Razat are foundations, stone alignments, and structural remnants whose exact functions remain uncertain. Some appear ceremonial. Others resemble storage platforms or hydraulic control features. Several orientations also seem deliberately aligned with terrain gradients and seasonal sunlight patterns. Water in ancient Arabia was not only a resource, it was deeply tied to political power and spiritual symbolism. Across the ancient Near East, springs often became sacred locations associated with divine protection, fertility, and survival. This creates another possibility. Ain Razat may have operated simultaneously as an engineering hub, caravan station, and ritual landscape. The blending of religion and hydraulic control was common throughout the ancient world. Egyptian temples controlled Nile irrigation cycles. Mesopotamian priesthoods regulated canal systems. Nabatean sacred spaces were integrated directly into water infrastructure. At Ain Razat, the separation between utility and spirituality may never have existed at all. Dolmen de Soto sits quietly beneath the hills of southwestern Spain, but archaeologists now consider it one of the most technologically puzzling megalithic structures in prehistoric Europe. Built nearly 5,000 to 5,500 years ago, during the late Neolithic period, the monument appears at first glance to be a simple stone tomb. But once excavations began, researchers discovered something far stranger: a perfectly aligned underground corridor, built with massive stones transported across difficult terrain, carved with mysterious symbols, engineered with unusual acoustic properties, and preserved with a structural stability that modern engineers still struggle to fully explain. The site is located near Trigueros in the province of Huelva, Andalusia. Although local farmers had known about unusual stones in the area for centuries, the monument was formally excavated in 1922 by the Spanish archaeologist Almendres de Soto, whose name the structure later adopted. What he uncovered was astonishing for its era: a stone corridor nearly 21 metres long leading toward a central burial chamber, constructed from dozens of upright megaliths weighing multiple tons each. The scale alone was extraordinary for a society that supposedly possessed only primitive stone tools, wood, rope, and human labour. What immediately confused artistic searchers was the geometric precision of the structure. The corridor maintains a remarkably straight axis, despite extending through uneven terrain. Modern surveys showed that the monument aligns closely with the sunrise during specific seasonal periods, particularly around the equinoxes. Similar astronomical alignments are famously seen at Newgrange and Stonehenge, but Dolmen de Soto differs because of its enclosed passage design. The sunlight does not merely illuminate the exterior. Under precise seasonal conditions, sunlight penetrates deep into the corridor itself, creating moving bands of light inside the monument. This suggests the builders understood solar positioning with surprising accuracy thousands of years before formal astronomy existed in Europe. The engineering problem becomes even more mysterious when the structure's length is considered. Maintaining alignment errors below only a few degrees over a 21-metre stone corridor without metal surveying equipment would have been extremely difficult even for later Bronze Age societies. Engineers studying ancient construction methods note that a small angular deviation at the entrance would produce a major misalignment by the end of the corridor. Yet Dolmen de Soto remains unusually symmetrical after surviving more than 5 millennia of erosion, ground movement, seasonal humidity changes, and temperature expansion. The stones themselves create another major mystery. Several megaliths inside the structure weigh between 10 and 20 tons. Geological studies indicate that not all of them originated immediately beside the monument, meaning prehistoric builders transported them across rugged terrain without wheeled vehicles or advanced draft animals. Experimental archaeology projects attempting to recreate similar transport methods using logs, ropes, and wooden sledges repeatedly encounter the same problem: directional control. Moving a 15-ton stone is possible under ideal conditions, but maintaining stability and precision placement across uneven ground becomes exponentially harder as mass increases. Researchers estimate that moving even a single large slab may have required more than 100 coordinated workers. Some calculations suggest friction reduction using wet clay, wooden rollers, or compacted earth paths, similar to theories proposed for Egyptian pyramid construction. But Dolmen de Soto presents an additional complication. Many stones were not only transported but erected vertically in narrow spaces with relatively even spacing and balanced pressure distribution. That indicates an advanced understanding of leverage, weight transfer, and structural balance long before classical engineering principles were formally documented. Inside the corridor, archaeologists uncovered dozens of carvings etched directly into the stone surfaces. Some depict human figures with oversized proportions. Others show daggers, zigzag patterns, solar symbols, and abstract geometric marks whose meaning remains uncertain. Unlike decorative art found in many later civilizations, these carvings appear strategically positioned within the monument. Certain engravings become far more visible only when sunlight enters at specific angles. This has led some researchers to argue that the monument functioned as a controlled ceremonial environment, where light itself became part of ritual activity. Comparisons with other European megalithic sites deepen the mystery. At Gavrinis Cairn, archaeologists discovered complex stone engravings aligned with chamber orientation. At Meishove, winter solstice sunlight enters deep into the tomb's interior. Dolmen de Soto appears to combine both concepts simultaneously. Astronomical alignment and symbolic interior carvings integrated into one engineered system. This suggests that Neolithic societies across Europe may have shared surprisingly advanced architectural ideas over enormous geographic distances. Another unresolved question involves the monument's acoustic behaviour. Modern acoustic tests inside the passage indicate that certain low-frequency sounds resonate unusually well within the enclosed stone corridor. Short vocal tones can produce prolonged echoes and standing wave effects not easily noticeable outside the structure. Similar acoustic anomalies have been documented at Newgrange and several prehistoric caves in France. Some neuroscientists studying ancient ritual spaces propose that repetitive low-frequency resonance may affect human perception and emotional states. If true, the builders may have intentionally designed enclosed stone spaces to manipulate sound psychologically during ceremonies. The structural durability of Dolmen de Soto may be the most difficult aspect to explain. Andalusia experiences seasonal thermal expansion, moisture fluctuation, and long-term erosion conditions capable of destabilizing ancient masonry. Yet much of the corridor remains standing after over 5,000 years. Engineers analysing megalithic architecture note that many stones were positioned to distribute vertical load outward instead of concentrating pressure directly downward. This reduces collapse risk by transferring weight laterally through the structure. Similar principles appear in later corbelled tombs and even Roman engineering, but Dolmen de Soto predates those civilizations by thousands of years. Archaeologists also discovered evidence that the monument underwent multiple phases of use. Human remains found inside indicate collective burials over long periods rather than a single ceremonial event. Stone tools, blades, and ritual objects suggest the site maintained cultural importance for generations. This raises a major sociological mystery. How could a supposedly primitive farming society organize the labour, food supply, planning, and long-term coordination necessary to construct and maintain such a massive ceremonial complex? Some anthropologists argue that monuments like Dolmen de Soto reveal the emergence of specialized knowledge classes within Neolithic Europe. Certain individuals may have possessed exclusive understanding of astronomy, stoneworking, seasonal cycles, and ceremonial traditions. In that sense, the monument may not simply represent a tomb, but an early centre of social power where engineering knowledge and spiritual authority became interconnected. Do you think Dolmen de Soto was simply a tomb, or evidence that prehistoric civilizations understood engineering and astronomy far better than we realise today? Share your thoughts in the comments below. Assos Necropolis lies on the Aegean coast of northwestern Turkey, where thousands of stone coffins once left one ancient city and spread across the Roman world. But the greatest mystery was never the dead buried inside them. It was the stone itself. Ancient writers claimed bodies placed inside these sarcophagi decayed with unnatural speed, reducing to skeletons in only a few weeks. More than 2,000 years later, archaeologists still debate whether Assos accidentally discovered a form of natural biochemical decomposition centuries before modern science understood bacteria, minerals, or microbiology. The ruins of Assos were systematically identified by European travellers during the 18th and 19th centuries, but major excavations accelerated after the American archaeological campaigns, led by Joseph Thatcher Clark and Francis H. Bacon in the 1880s. As excavators cleared the necropolis surrounding the ancient city, they uncovered hundreds of massive stone sarcophagi carved from local volcanic andesite. Many were unfinished, others appeared prepared for export. What emerged was not simply a cemetery, but evidence of a large-scale industrial stone operation connected to Mediterranean trade routes more than 2,000 years ago. The first and most disturbing mystery became known in antiquity itself. Roman naturalist Pliny the Elder described Assos stone coffins as sarcophagi, literally flesh-eating stones. According to ancient accounts, corpses buried inside decomposed unusually fast, sometimes leaving only bones within roughly 40 days. While ancient writers often exaggerated, the persistence of the claim across multiple Roman sources suggests the phenomenon was widely observed rather than invented mythology. Modern geology offers partial explanations but not complete certainty. The sarcophagi were carved from volcanic andesite rich in minerals and microscopic pore networks. Unlike dense marble, porous volcanic stone can absorb moisture and accelerate airflow around organic material. Some researchers believe the rock may have created conditions favourable for aerobic bacterial activity, dramatically increasing decomposition rates. In effect, the stone may have functioned as a natural dehydration chamber combined with microbial acceleration. What makes this extraordinary is the historical context. Ancient civilizations usually obsessed over preserving bodies. Egyptians spent nearly 3,000 years refining mummification techniques designed to stop decay entirely. Natron salts removed moisture while resins sealed tissue against bacteria. Yet Assos appears to represent the opposite philosophy, accelerating destruction instead of preventing it. Two ancient cultures separated by geography and belief, both manipulated decomposition with remarkable effectiveness, one slowing time, the other speeding it up. Even today, forensic decomposition rates vary enormously depending on humidity, temperature, bacteria, oxygen, and soil chemistry. In modern outdoor conditions, full skeletal reduction can take months or years. Under dry desert conditions, tissue may naturally mummify instead of decomposing. Yet the Assos reputation persisted strongly enough that wealthy Romans imported these coffins across the Mediterranean specifically for burial. That implies the effect was visible enough to become commercially valuable. The second mystery involves the stoneworking itself. Andesite is significantly harder than limestone and much more difficult to carve. On the Mohs hardness scale, andesite often approaches hardness levels near basalt, meaning tools wear down rapidly during cutting. Yet Assos craftsmen produced enormous sarcophagi with relatively smooth interior walls, sharply cut edges, and fitted lids weighing multiple tons. Some unfinished examples reveal systematic quarrying methods rather than random carving. Workers appear to have separated blocks using channels and controlled fracture lines before shaping the coffins with iron chisels and hammerstones. The precision becomes difficult to explain at industrial scale. Producing a single massive coffin would already require immense labour. Assos produced hundreds. The logistics become even more mysterious when examining distribution patterns. Archaeologists have identified Assos sarcophagi far beyond the city itself, including sites in Alexandria, the Levant, Anatolia, and parts of the Balkans. Transporting multi-ton volcanic coffins through mountainous terrain toward coastal ports would have required advanced coordination systems. Even modern engineers recognize the difficulty of moving concentrated stone loads without cranes, hydraulic lifts, or mechanized transport. Ancient Roman merchant ships could carry heavy cargo, but loading operations remained difficult to reconstruct. Some historians believe large wooden treadwheel cranes may have been used in harbour zones, powered entirely by human walking motion inside rotating wheels. Others argue that ramps, rollers, sledges and compound pulley systems distributed the loads gradually. Yet no surviving written manual explains exactly how Assos exported stone coffins at such scale. Comparisons with other ancient transport mysteries are unavoidable. The unfinished obelisk at Aswan weighs more than 1,000 tons and demonstrates Egyptian stone-cutting ambition. The trilithon blocks of Baalbek each exceed 800 tons and still challenge modern explanations. Easter Island's Moai statues were transported across volcanic terrain using methods researchers continue debating today. Assos belongs to the same category of ancient engineering paradoxes. Societies with supposedly limited technology repeatedly handling materials modern construction teams would still respect. Another unresolved mystery surrounds the necropolis layout itself. In many ancient cities, the dead were deliberately positioned along approach roads so travelers entering the city would confront generations of ancestors before reaching the living population. At Assos, sarcophagi lined major access routes overlooking the Aegean Sea. Death became part of the urban landscape. Some archaeologists suspect this arrangement also served commercial purposes. Foreign merchants arriving by sea would immediately see enormous stone coffins displayed outside the city walls, effectively advertising Assos craftsmanship before trade negotiations even began. The necropolis may have functioned simultaneously as cemetery, monument, and industrial showroom. Environmental durability adds another layer of mystery. Assos sits within an active seismic region exposed to salt air, humidity shifts, and strong Aegean winds. Over 2 millennia, many softer stone structures across the Mediterranean suffered catastrophic erosion. Sandstone monuments at Petra lost enormous surface detail due to wind abrasion and water infiltration. Yet numerous Assos sarcophagi remained structurally recognizable despite constant coastal exposure. Geologists believe the volcanic composition of the andesite contributed to this survival. Fine-grained igneous rock often resists weather penetration better than porous sedimentary stone. However, durability alone does not fully explain the preservation quality. Some lid joints remain surprisingly stable despite centuries of earthquakes affecting western Anatolia. The industrial implications may be the most overlooked mystery of all. Assos was not merely carving isolated luxury tombs. Evidence suggests organized extraction zones, standardized coffin forms, labor specialization, and export coordination across international trade networks. In other words, the city operated something resembling a proto-industrial stone manufacturing economy centuries before the Industrial Revolution. That raises uncomfortable historical questions. Ancient societies are often imagined as technologically primitive compared to the modern world. Yet places like Assos repeatedly reveal systems of engineering organization, resource management, and material science that appear far more advanced than simplistic historical narratives suggest. The workers of Assos understood quarry stress, transport balance, stone durability, and decomposition behavior well enough to create products desired across an empire stretching thousands of kilometers. Do you think the people of Assos truly understood the strange properties of these flesh-eating stones? Or was it an ancient discovery they used without ever knowing the science behind it? Share your thoughts in the comments below. Dry highlands in central Turkey, nearly 1,500 meters above sea level, conceal enormous stone walls stretching across the Anatolian plateau like the remains of a forgotten fortress city. For centuries, these ruins were believed to belong to a relatively minor settlement. That changed in the late 20th century when archaeologists began systematic surveys using aerial photography, satellite imaging, and large-scale geomagnetic scanning. What emerged beneath the soil shocked researchers. Hidden under the landscape was an enormous planned city covering nearly 2.5 square kilometres, surrounded by more than 7 kilometres of defensive walls, reinforced by hundreds of towers and gates. The city appeared to have been built rapidly during the 6th century BCE and then destroyed by fire only a short time later. Unlike most ancient cities that evolved gradually over centuries, Kerkenez seemed to appear almost fully formed from the beginning. That single detail transformed the site into one of the strangest archaeological mysteries in Anatolia. The first mystery surrounding Kerkenez is the sheer speed and scale of its construction. Archaeologists estimate that the outer fortification walls alone required millions of stones. Some wall sections were more than 4 meters thick, extending across rugged hills and steep terrain with remarkable consistency. For comparison, many fortified Iron Age cities in Anatolia, far smaller and developed incrementally over generations. Kerkenez, however, resembles a sudden state engineering project more comparable to imperial capitals of Assyria or later Persian administrative centres. The logistical problem becomes almost difficult to comprehend. Without cranes, industrial metal tools, or wheeled transport systems capable of handling heavy stone efficiently across mountainous terrain, ancient builders somehow organised labour, quarrying, transport and construction on a gigantic scale. Researchers studying labour estimates suggest that, even with thousands of workers operating simultaneously, construction may have required an extremely centralised authority with advanced planning systems. The city's uniformity strongly implies pre-designed urban engineering rather than organic growth. That level of coordination in Iron Age Anatolia remains deeply unusual. Kerkenez does not merely look defensive, it appears engineered entirely around military logic. The walls zigzag across the plateau instead of following simple straight lines, creating overlapping defensive angles that allowed defenders to attack invaders from multiple directions simultaneously. Many medieval fortresses later adopted similar principles, yet Kerkenez demonstrates them centuries earlier. The gates are equally mysterious. Instead of wide, direct entrances, several access points force movement through narrow turning passages where invading forces would become trapped and exposed. Archaeologists believe these choke point systems were intentionally designed to maximize defensive advantage. What makes this strange is that neighboring cultures of the same era often relied on much simpler defensive architecture. Kerkenez suggests a society with unusually advanced understanding of battlefield geometry and controlled urban defense. Some researchers even compare the city's layout to a giant engineered security system rather than a conventional settlement. One of the most revolutionary aspects of Kerkenez is how modern technology revealed the city without excavation. Archaeologists used magnetometry surveys capable of detecting buried stone structures and burnt materials beneath the ground. The results exposed an entire hidden urban grid. Streets, districts, compounds, workshops, and ceremonial areas appeared with astonishing clarity. The scans revealed something even more puzzling. The city followed a highly organised plan. Roads intersected in controlled patterns, major structures occupied strategic positions, and the urban design appeared coordinated across the entire settlement. Ancient cities usually evolve unevenly over centuries, producing chaotic layouts. Kerkenez instead resembles a modern planned capital, designed from the beginning according to a master blueprint. This raises a disturbing historical question. If Iron Age builders in Anatolia could organise urban planning at this level, how many other primitive civilizations may have possessed forms of engineering sophistication that archaeology still underestimates? At some point in the 6th century BCE, Kerkenez was consumed by a massive fire. Thick destruction layers and burned debris appear across large sections of the city. Yet the most mysterious detail is what happened afterward. Almost nothing. Most strategically located ancient cities were rebuilt repeatedly after destruction. Troy was reconstructed multiple times. Babylon survived successive invasions. Hattusa rose and fell across different eras. Kerkenez, however, was largely abandoned forever. This is extremely unusual considering its enormous walls and dominant position overlooking the Anatolian plateau. Archaeologists still debate whether the city was destroyed during warfare, internal collapse, or deliberate evacuation followed by systematic burning. Some theories connect the destruction to the expansion of the Persian Empire under Cyrus the Great, while others associate it with regional political collapse. But no explanation fully clarifies why such an enormous and expensive city vanished almost instantly from history. Another unresolved mystery is sustainability. Kerkenez stood in a relatively harsh environment where maintaining a large urban population would have been difficult. Ancient cities depended entirely on reliable supplies of water, timber, grain, livestock and fuel. Yet evidence suggests Kerkenez may have supported thousands of inhabitants within fortified walls. The engineering challenge becomes enormous when compared to similar settlements. Researchers estimate that ancient urban populations required vast quantities of food transported constantly from surrounding agricultural zones. Water management alone would have been critical. However, archaeologists have not fully explained how Kerkenez sustained itself logistically during its short existence. This has led some historians to propose that Kerkenez may not have functioned as a traditional permanent city at all. Instead, it may have operated as a massive military administrative centre or emergency royal capital designed for strategic control during periods of regional instability. If true, the city may represent one of the earliest examples of large-scale temporary geopolitical engineering in ancient Anatolia. Several parts of Kerkenez appear aligned carefully with the surrounding terrain and defensive sightlines. Elevated structures command wide views over the plateau, while road systems seem optimized for controlled movement across the city. This level of urban precision is particularly strange because it emerged in an era supposedly limited by relatively primitive surveying methods. Ancient engineers likely relied on ropes, wooden measuring rods, solar observations, and manual geometry. Yet the resulting city demonstrates remarkable consistency across enormous distances. Comparisons are often made with other ancient planned cities such as Mohenjo-Daro in the Indus Valley or the orthogonal street systems later perfected by the Romans. However, Kerkenez differs because it combines planned urbanism with extreme militarization. The city feels less like a civilian settlement and more like a giant strategic instrument embedded directly into the landscape. Perhaps the greatest mystery is the identity of the people who built it. Some archaeologists associate Kerkenez with the Medes, an Iranian people who briefly dominated parts of Anatolia before the Persian Empire emerged. Others argue the city may represent a local Anatolian power attempting to imitate imperial models from Assyria and Mesopotamia. The uncertainty matters because Kerkenez seems too ambitious for an ordinary regional kingdom. Building a city of this scale required immense labour organisation, political authority, engineering knowledge, and economic resources. Whoever constructed Kerkenez possessed capabilities far beyond what historians once assumed for Iron Age Anatolia. And yet the civilization behind the city left surprisingly little written evidence. No surviving inscriptions fully explain its purpose, rulers, or sudden destruction. The city remains largely silent. What do you think Kerkenez really was? A forgotten imperial capital, a giant military experiment, or evidence that ancient engineering was far more advanced than we realise? Share your thoughts in the comments below. Sirwah ancient city was discovered in the desert highlands west of Marib in Yemen, positioned along the ancient incense trade routes that once connected southern Arabia to the Mediterranean world. Archaeologists began major excavations in the 20th century, uncovering massive stone temples, fortified walls, hydraulic systems, and long inscriptions written in the ancient Sabaean Musnad script. What shocked researchers was not simply the age of the city, estimated at more than 2,500 years old, but the level of engineering hidden beneath one of the harshest environments on Earth. Annual rainfall in this region can fall below 100 millimeters. Temperatures regularly exceed 40 degrees Celsius, and yet Sirwah once supported a stable urban population connected to one of the largest hydraulic civilizations in the ancient world. The first mystery surrounding Sirwah is how such a complex stone city was constructed in an environment with almost no natural conditions favourable for large-scale architecture. Many of the surviving walls consist of enormous limestone and granite blocks weighing several tons each. Some joints between stones remain remarkably tight even after centuries of earthquakes, erosion and warfare. Unlike Roman construction, which often relied heavily on mortar and concrete, parts of Sirwah appear to use carefully balanced dry stone techniques similar to those later seen in Inca sites such as Sacsayhuaman in Peru. Engineers studying ancient load distribution systems have noted that irregular polygonal stone fitting can absorb seismic stress more effectively than rigid uniform masonry. That raises a major question. How did the Sabaeans understand structural flexibility thousands of years before modern earthquake engineering? The transportation problem becomes even more difficult when examining the geography around Sirwah. The surrounding terrain is rocky, mountainous and extremely dry. There is little evidence for large forests capable of supplying massive wooden rollers or cranes, like those used in parts of ancient Rome. Some historians estimate that moving a single 10-ton stone block across desert terrain with primitive tools could require hundreds of labourers. Yet Sirwah contains dozens of such stones positioned with surprising precision. Comparisons are often made to the construction mysteries of Petra in Jordan or the Nabatean desert fortresses, but Sirwah predates many later Arabian engineering traditions. Even more puzzling is the lack of clear evidence showing exactly how the heaviest blocks were lifted and aligned. The greatest mystery of Sirwah may be its relationship to water. The city stood near the legendary Marib Dam, one of the most ambitious hydraulic projects of the ancient world. Ancient sources and archaeological evidence suggest that the dam system irrigated thousands of hectares of farmland in one of the driest parts of Arabia. Some estimates suggest the broader irrigation network may have supported tens of thousands of people. Sirwah appears to have functioned as part of this larger hydraulic system, possibly serving as a control centre or regional distribution point. Archaeologists discovered channels, reservoirs and stone-lined waterways near the city, many constructed with gradients so precise that water could travel long distances without destroying the channels through overflow or stagnation. Modern hydraulic engineers understand that even small errors in slope can destabilize irrigation systems, especially in arid climates where evaporation rates are extremely high. In Roman aqueduct systems, gradients often averaged only a few centimeters per 100 meters. Evidence from southern Arabia suggests the Sabaeans achieved similarly controlled water movement centuries before Roman hydraulic expansion reached its peak. This has created one of the most controversial debates surrounding Sirwah. Did the Sabaeans independently develop advanced hydrological knowledge equal to or even surpassing some Mediterranean civilizations of the same era? researchers have compared aspects of the Marib-Sirwah irrigation network to Persian qanat systems, Roman aqueducts, and Nabatean water harvesting systems at Petra. Yet Sirwah's environment was arguably harsher than all of them. Maintaining long-term agriculture in such conditions would have required deep understanding of seasonal flooding, sediment control, evaporation management, and pressure distribution. Another mystery lies within the inscriptions carved into stone throughout Sirwah. Some of the most famous inscriptions belong to King Karibil Watar, a ruler associated with military expansion and major construction projects. What makes these inscriptions unusual is that many appear administrative rather than purely religious. They reference campaigns, infrastructure, alliances, and dedications tied to large public works. Historians studying ancient state formation believe this indicates the Sabaeans possessed a surprisingly advanced bureaucratic system capable of organizing labor, managing resources, and maintaining regional infrastructure. This becomes even more significant when compared to other ancient civilizations. Large hydraulic systems historically required centralized administration. Ancient Egypt depended on Nile flood management. Mesopotamian cities relied on canal maintenance. The Roman Empire used extensive bureaucracies to sustain roads and aqueducts. Sirwah suggests that southern Arabia may also have developed a sophisticated administrative engineering state that history has largely ignored. The city's temple structures introduce another unexplained layer. Several temples appear aligned with solar movements and seasonal cycles. While astronomical alignments are common in ancient architecture, researchers suspect the alignments at Sirwah may have had practical environmental purposes. In desert societies, predicting seasonal rainfall and flood cycles could determine survival. Some scholars argue that astronomy in southern Arabia was not merely religious symbolism but part of environmental management. If true, Sirwah represents a civilization where astronomy, engineering, agriculture, and political authority were deeply interconnected. The durability of the city itself remains another unresolved puzzle. Yemen experiences severe temperature fluctuations between day and night, conditions that gradually fracture stone through thermal expansion and contraction. Despite this, many Sirwah structures survived for over 2 millennia. Some modern concrete structures in the region deteriorate faster than these ancient stone walls. Materials scientists studying ancient construction techniques have proposed that the specific stone selection, interlocking geometry, and stress distribution methods used by Sabaean builders created unusually resilient structures capable of surviving both seismic activity and extreme climate cycles. One particularly strange aspect is how little of the Sabaean technological tradition survived historically. Ancient Yemen once controlled the lucrative frankincense and myrrh trade, generating enormous wealth from routes extending toward the Mediterranean, East Africa, and possibly India. Sirwah stood directly within this network, yet after the decline of the Marib Dam system, much of the civilization rapidly faded from power. Some historians believe repeated dam failures triggered agricultural collapse across the region. Others point to climate change, warfare, or shifting maritime trade routes that bypassed inland caravan cities. But the collapse itself raises disturbing parallels to modern civilization. Sirwah appears to demonstrate how highly interconnected infrastructure systems can become catastrophically vulnerable when a central hydraulic network fails. If the irrigation systems collapsed, agriculture failed. If agriculture failed, trade routes weakened. If trade weakened, political authority fragmented. In that sense, Sirwah may represent one of history's earliest examples of infrastructure dependency causing civilizational collapse. Do you think the Sabaeans truly developed engineering knowledge far beyond their time? Or are we still missing a major piece of the story behind Sirwah? Share your thoughts in the comments below. Among the barren mountain valleys of Egypt's eastern desert, around 35 kilometers southeast of Aswan, archaeologists uncovered one of the most mysterious industrial sites of the ancient world. The area was first seriously documented during the late 19th and early 20th centuries after explorers discovered hundreds of inscriptions, ruined settlements, military outposts and ancient mining tunnels scattered across the desert landscape. What initially appeared to be isolated ruins soon revealed something far more unusual. A massive industrial mining network operating nearly 4,000 years ago in one of the harshest environments on Earth. Temperatures in this region regularly exceed 45 degrees Celsius during summer. Annual rainfall is close to zero. Yet archaeologists uncovered evidence that large Egyptian expeditions repeatedly crossed this desert during the Middle Kingdom, particularly under rulers such as Senusret I, Senusret III, and Amenemhat III. More than 1,200 inscriptions have been identified at the site, many recording organised mining expeditions involving soldiers, officials, workers, stonecutters, scouts, and water carriers. The scale immediately raised a difficult question. How did a Bronze Age civilization sustain large industrial operations in terrain where survival itself is extremely difficult even today? The greatest mystery surrounding Wadi el-Hudi is not the amethyst itself, but the logistics required to obtain it. The mines are located far from the Nile River, meaning every drop of water, every food supply, every tool, and every worker had to travel through hundreds of kilometers of hostile desert terrain. Some inscriptions describe expeditions involving several hundred men. Even under conservative estimates, an expedition of 300 workers would require several tons of water per week merely to survive. Modern desert survival studies estimate that humans performing heavy labour in temperatures above 40 degrees Celsius may require 10 to 15 litres of water daily. This means Egyptian expeditions may have needed thousands of litres transported continuously across barren rock valleys with no stable wells nearby. What makes this harder to explain is the consistency of the operations. Wadi el-Hudi was not used once or twice. Archaeological evidence suggests repeated industrial activity across centuries. Defensive walls, storage buildings, guard posts, worker settlements, and road systems indicate long-term logistical planning rather than temporary exploration. Some researchers compare this organisational complexity to later Roman mining systems in Spain and Britain. Despite Wadi el-Hudi predating many Roman industrial operations by more than 1,500 years. Others argue that the Egyptians may have created hidden desert supply stations or seasonal water caches that remain undiscovered today. The amethyst veins at Wadi el-Hudi were embedded inside extremely hard metamorphic rock. Yet many ancient tunnels display narrow precision cuts and deep extraction chambers carved directly into the mountains. This creates a technological problem. During the Middle Kingdom, Egyptian miners supposedly relied primarily on copper chisels, dolerite hammerstones, wooden wedges and fire-setting techniques. However, pure copper ranks only around 3 on the Mohs hardness scale, while quartz-based minerals approach hardness levels near 7. In simple terms, the stone being mined was significantly harder than the tools supposedly used to shape it. Similar engineering contradictions appear elsewhere in Egypt, especially at the granite quarries of Aswan and inside certain Old Kingdom stone structures. At Wadi el-Hudi, some tunnel walls contain extraction marks that appear unusually consistent, suggesting advanced control during cutting operations in confined underground spaces. Researchers believe miners may have combined thermal fracturing with repeated percussion methods to weaken the surrounding rock before extracting the amethyst. But even this does not fully explain the efficiency of the operation. Some tunnels penetrate deep into unstable rock zones with surprisingly organised layouts, indicating careful geological understanding rather than random digging. One of the strangest aspects of Wadi el-Hudi is the apparent geological accuracy of the mining expeditions. Ancient miners repeatedly located productive amethyst veins hidden within remote mountain systems across the eastern desert. Even with modern surveying technology, locating mineral veins in desert mountain environments remains difficult and expensive. Yet Egyptian expeditions consistently identified profitable extraction zones long before modern geology existed as a science. Some archaeologists believe generations of accumulated observational knowledge allowed miners to recognize subtle surface indicators such as rock coloration, fracture patterns, or mineral traces. Others suggest the Egyptians developed surprisingly sophisticated practical geology through centuries of experimentation. The accuracy becomes even more remarkable when compared with many medieval mining operations, which often relied heavily on luck and shallow excavation. At Wadi el-Hudi, Egyptian miners repeatedly targeted productive areas with unusual precision. The eastern desert is one of the easiest places on Earth to become lost. Large areas contain nearly identical rocky valleys, dry riverbeds, and barren mountain ridges extending for hundreds of kilometers. Yet ancient expeditions repeatedly traveled between the Nile Valley and Wadi el-Hudi with remarkable consistency. Archaeologists have identified ancient pathways, guard stations, and travel routes connecting the mines to the Nile trade network. Without compasses, modern maps, satellites, or GPS, Egyptian desert travelers somehow maintained accurate navigation across terrain, where even experienced modern hikers can lose orientation quickly. Some historians believe they relied on solar positioning, stars, mountain silhouettes, and memorized route systems passed between expedition leaders. But the efficiency of the surviving road network suggests something more systematic. Certain routes appear optimized to reduce exposure to heat while maximizing access to defensible terrain and possible water sources. This implies advanced environmental knowledge accumulated through long-term desert exploration. Another mystery involves the militarized nature of the site. Wadi el-Hudi was not merely a mine, it functioned almost like a fortified industrial colony. Archaeologists discovered defensive walls, watchtowers, narrow entry checkpoints, and strategically positioned guard posts overlooking mountain passes. Some forts were built at elevated positions capable of monitoring approaching travelers from long distances. This level of military infrastructure suggests the Egyptians considered the amethyst mines strategically important. Inscriptions reference desert raiders and hostile nomadic groups capable of attacking mining expeditions. Protecting the mines therefore required constant military oversight. What surprises researchers is how effectively the defences used natural terrain. Many structures were positioned to exploit narrow canyon entrances and elevated sightlines, resembling military principles later seen in Roman frontier forts and medieval mountain fortifications. Modern audiences often underestimate the importance of amethyst in ancient Egypt. During the Middle Kingdom, high-quality purple stone was associated with royalty, elite jewellery, religious symbolism, and political power. Before large amethyst deposits were discovered elsewhere in later centuries, Egyptian amethyst was considered extremely rare. Some historians compare its prestige value to lapis lazuli in Mesopotamia, or jade in ancient China. The willingness to risk large expeditions through lethal desert conditions suggests the stone carried enormous economic and symbolic importance. Certain royal ornaments, scarabs, necklaces, and ceremonial objects used amethyst imported directly from Wadi el-Hudi. Yet despite the immense investment, historians still debate whether the true value of the site was purely decorative. Some theories propose that control of luxury resources played a critical role in maintaining royal legitimacy and elite political networks across Egypt. One overlooked mystery is the durability of the site itself. Desert environments create intense thermal stress. Rock and mud brick structures experience rapid expansion during daytime heat and contraction during freezing desert nights. Over centuries, these thermal cycles normally destroy ancient buildings. Yet many walls, pathways and structural remains at Wadi el-Hudi survived for nearly 4,000 years. This suggests Egyptian builders understood how to construct architecture adapted specifically for desert geology and temperature variation. Certain walls appear positioned to minimize erosion from flash floods moving through seasonal wadis, while settlement layouts reduced direct exposure to prevailing desert winds. Even today, engineers designing structures in arid climates must carefully calculate thermal expansion and material fatigue. The survival of these ancient installations suggests a practical environmental engineering knowledge far beyond what is often associated with Bronze Age societies. Do you think the people of ancient Egypt possessed engineering knowledge far more advanced than history officially admits? Share your thoughts and theories in the comments below. Dry plains southeast of Tehran, Iran hide one of the largest mud brick fortresses ever built in the ancient world, Rayan Castle. The site was first identified through early archaeological surveys of the Varamin region, but its true scale only became clear through aerial photography and satellite imaging in the late 20th century. Researchers discovered that the massive enclosure stretched nearly 1.8 to 2 kilometers around its perimeter, covering roughly 200 hectares. That made Rayan Castle larger than many Roman frontier forts, and even comparable to sections of major fortified cities from late antiquity. Yet despite its enormous scale, much of the structure remained hidden beneath layers of dust, erosion, and desert terrain for centuries, causing one of ancient Persia's greatest engineering projects to almost disappear from history entirely. The first mystery begins with the walls themselves. Rayan Castle was constructed primarily from mud brick and rammed earth, materials normally considered fragile compared to stone. In most environments, mud brick structures collapse rapidly under rain, flooding, earthquakes, or thermal stress. Yet parts of Rayan Castle have survived for nearly 1,500 years in one of the harshest climates in the Middle East. The walls originally stood several meters high and were built with extraordinary thickness, in some places estimated at over 17 to 22 meters at the base. Modern engineers studying ancient earthen architecture have noted that such dimensions were far beyond what was necessary for ordinary settlement defense. The structure appears massively over-engineered, almost as if its builders expected prolonged siege warfare or extreme environmental stress. Researchers comparing the site to Roman, Byzantine and Central Asian fortifications notice something even stranger. The internal composition of the walls may have involved layered engineering techniques far more advanced than previously believed for the Sassanid period. Samples from surviving sections suggest the builders may have mixed clay with lime compounds, mineral salts, organic fibers, and possibly volcanic ash-like silicates. Similar stabilizing techniques appear in a Roman concrete, Persian sarouge waterproof mortar, and some pre-Columbian adobe structures in Peru. These additives reduce cracking, improve thermal resistance, and increase cohesion between layers. What makes Rayan Castle unusual is that many damaged sections did not collapse catastrophically, even after severe erosion. Instead, the walls often deformed gradually while maintaining structural continuity, behaving more like engineered compressed earth systems than simple mud construction. The climate around Varamin creates violent temperature swings between scorching daytime heat and cold desert nights. Modern rammed earth architecture often struggles under such repeated expansion and contraction cycles, unless reinforced with contemporary stabilizers. Yet Rayan Castle endured these stresses for centuries. Some archaeologists suspect the builders intentionally controlled moisture levels between construction layers to create differential compression zones capable of absorbing thermal expansion. If true, it would imply a practical understanding of material behavior that resembles principles used in modern geotechnical engineering. No written Sassanid engineering manuals describing such techniques have survived, making the knowledge behind the fortress largely invisible to history. Another major mystery lies in the fortress layout. Rayan Castle contained more than 140 semicircular defensive towers positioned at highly regular intervals around the perimeter. Military historians studying reconstructed models noticed that the towers created overlapping lines of sight and projectile coverage, remarkably similar to defensive kill zone concepts used in medieval and early modern fortress design. The arrangement minimized blind spots while allowing defenders to move rapidly between sectors. This is particularly surprising because the fortress predates many famous European military fortification principles by centuries. Some analysts compared the defensive geometry to later Byzantine and even Renaissance-era concepts of angular defense, despite the fact that Sassanid armies primarily fought with archers, cavalry and infantry rather than gunpowder artillery. Satellite mapping has revealed that the fortress gates were positioned with unusual strategic logic as well. Access points appear designed to slow invading forces while maximizing defensive visibility from nearby towers. The internal road alignments may also have been optimized for rapid troop movement and logistical coordination. Several researchers have argued that Rayan Castle functioned less like a conventional castle and more like a massive military refuge or emergency defensive city capable of protecting large civilian populations during invasion. This theory aligns with the geopolitical instability of the late Sassanid Empire, when Persia faced repeated wars against the Byzantine Empire, as well as threats from Central Asian nomadic groups. But this raises another difficult question. If Rayan Castle was truly intended to shelter tens of thousands of people, how could such a population survive in a semi-arid environment? The region surrounding the fortress does not naturally support massive urban populations without sophisticated water management. Archaeologists suspect the existence of Qanat systems, underground channels used throughout ancient Persia to transport groundwater over long distances with minimal evaporation. However, only fragments of possible hydraulic infrastructure have been identified near the site. If a full Qanat network once existed beneath or around the fortress, much of it may remain buried or destroyed. Without reliable water distribution, the enormous enclosure would have been impossible to sustain during siege conditions. Food logistics present an equally puzzling problem. Ancient military calculations suggest that even a modest defensive population of 20,000 people would require enormous grain storage capacity and carefully coordinated supply systems. Some buried areas inside the fortress may contain warehouses, storage chambers, or administrative complexes, but only limited excavation has been conducted. The sheer scale of unexplored terrain means much of Rayan Castle remains archaeologically unknown. Ground-penetrating surveys indicate that significant structural remains still lie beneath accumulated sediment. In many ways, researchers may currently understand only the outer shell of the complex, while the true internal organization remains hidden underground. Earthquakes create another layer of mystery. Iran sits on multiple active tectonic fault systems, and many ancient mud brick settlements across the region were destroyed repeatedly by seismic activity. Yet large portions of Rayan Castle continued standing long after neighbouring structures vanished. Some engineers believe the unusually wide foundations and layered earth composition may have helped absorb seismic energy through controlled deformation. Similar concepts appear in earthquake-resistant Inca masonry and certain Japanese earthen wall systems. Instead of resisting movement rigidly like stone, the fortress may have survived by flexing and redistributing stress through its enormous mass. If accurate, this would represent one of the oldest large-scale examples of passive seismic engineering ever identified in ancient architecture. The dating of the fortress also remains debated. Most scholars associate the structure with the Sassanid Empire between the 3rd and 7th centuries CE, but some evidence hints that portions of the site may incorporate older foundations or earlier defensive traditions. The Sassanids were among the most technologically advanced empires of late antiquity, famous for hydraulic engineering, large-scale urban planning, and military organisation. Even so, the dimensions of Rayan Castle exceed what many historians previously assumed possible for mud brick military construction during the period. Comparisons with Roman forts along the Rhine or Hadrian's Wall show that while Rome specialised in stone engineering, the Persians may have mastered large-scale earth architecture with an efficiency still underestimated today. Modern drone surveys continue revealing unusual traces around the fortress. Some researchers believe secondary defensive lines or buried structures may still exist around the main enclosure. What makes the site even more mysterious is that very little evidence of permanent residential activity has been found inside the massive fortress. This has led to theories that Rayan Castle may have functioned as an emergency defensive refuge, used temporarily during wars or invasions rather than as a constantly occupied city. The western coast of the Red Sea in eastern Egypt holds one of the most unexpected discoveries from the ancient world. Ain Sukhna preserves evidence of a functioning industrial harbour operating more than 4,500 years ago in one of the harshest environments on Earth. Archaeologists uncovered mining tunnels, ship equipment, copper transport systems, storage galleries, furnaces, administrative seals, and evidence of organised maritime expeditions existing centuries before most civilizations had developed large-scale seafaring infrastructure. The deeper researchers investigated the site, the less it resembled a primitive outpost, and the more it began to look like a lost industrial network far ahead of its time. Modern excavations at Ain Sukhna intensified during the late 1990s and early 2000s through French-Egyptian archaeological missions led by researchers including Pierre Tallet and Gregory Marouard. What initially appeared to be isolated ruins soon revealed enormous rock-cut galleries, harbour facilities, storage systems, ancient inscriptions, anchors, ship components, and evidence of repeated royal expeditions dating primarily to Egypt's 4th and 5th dynasties. Radiocarbon analysis, pottery studies, and inscriptions connected the site directly to Old Kingdom operations, roughly between 2600 and 2200 BCE, the same era associated with the construction of the Great Pyramids. That timeline created an immediate mystery. If the Egyptians could organize industrial-scale maritime logistics here during the Pyramid Age, then their technological and administrative capabilities may have been far more advanced than traditionally believed. Ain Sukhna sits beside an arid coastal desert where summer temperatures regularly exceed 40 degrees Celsius, while fresh water sources remain extremely limited. Strong winds, salt corrosion, and unstable terrain make long-term settlement difficult even today. Yet archaeological evidence suggests the site functioned repeatedly for centuries. Researchers uncovered massive storage galleries carved directly into mountains, large ceramic storage jars, food remains, rope fragments, harbour equipment, copper-related industrial debris, and living quarters for labourers and sailors. The logistical implications are enormous. Maintaining hundreds of workers in this environment would have required continuous transport of water, food, timber, fuel, tools, and medical supplies across desert routes stretching dozens of kilometres from the Nile Valley. Ancient Egypt is often portrayed as a civilization concentrated almost entirely around the Nile River, but Ain Sukhna reveals something very different, a state capable of projecting organised industrial activity deep into hostile terrain. Some archaeologists compare its logistical complexity to later Roman mining and harbour systems, despite being constructed nearly 2,000 years earlier, suggesting that Old Kingdom Egypt may have operated with a level of organisation far beyond traditional historical assumptions. One of the most astonishing discoveries at Ain Sukhna was the enormous network of galleries carved directly into the surrounding mountains. Some galleries extend more than 20 metres into solid rock, while others contain interconnected chambers apparently designed for storage, workshops, and expedition equipment. The engineering problem becomes obvious immediately. Old Kingdom Egypt supposedly relied primarily on copper chisels, stone pounders, wooden wedges and manual labour, yet these galleries were excavated into extremely hard geological formations with surprising structural stability. Unlike natural caves, the tunnels displayed deliberate organisation through flattened floors, controlled entrances, internal storage divisions, smoke-blackened ceilings from industrial activity, and evidence of repeated occupation phases. Researchers still debate how efficiently these tunnels could have been excavated using only known Old Kingdom tools. Experimental archaeology has demonstrated that cutting hard stone with copper tools alone is painfully slow, with some estimates suggesting that removing even 1 cubic metre of hard rock could require hundreds of labour hours, yet Ain Sukhna contains an entire complex of galleries. This raises difficult questions about whether Old Kingdom workers possessed more advanced quarrying techniques than historians currently understand, whether they exploited thermal fracturing methods using fire and cold water, or whether the Egyptian state simply had the ability to mobilise labour on a scale far greater than previously estimated. The Red Sea is not an easy body of water to navigate. It contains dangerous reefs, unpredictable currents, seasonal winds, and extreme coastal heat. And even later civilizations struggled with sustained navigation there. Yet Ain Sukhna proves that Old Kingdom Egyptians were already conducting organised maritime expeditions across these waters over 4,500 years ago. Archaeologists uncovered stone anchors, ship timbers, rope systems, dismantled boat components, harbour installations, and repair zones that collectively point towards surprisingly advanced maritime operations. Some evidence suggests Egyptian ships may have been disassembled near the Nile, transported across desert routes in sections, then reassembled at Red Sea ports before sailing towards Sinai. That process alone required astonishing organisational precision. A medium-sized wooden vessel would have required several tons of timber, rope, linen, sailcloth, wooden pegs, and coordinated manpower, while every component had to survive desert transport without warping or breaking under extreme heat. This directly contradicts the outdated image of Old Kingdom Egypt as a civilization limited primarily to river transport. At Ain Sukhna, they appear capable of planned open-water maritime operations centuries before many comparable Bronze Age societies developed similar systems. The most fascinating mystery at Ain Sukhna centres on copper. During the Old Kingdom, copper was one of the most strategically important materials in Egypt because it was essential for tools, chisels, drills, saws, weapons, ship fittings, and large-scale stoneworking projects including pyramid construction. Many expeditions launched from Ain Sukhna were likely connected directly to the copper mines of Sinai, and this is where the technological mystery becomes extraordinary. Copper ore had to be mined in Sinai, transported across harsh terrain, loaded onto ships, carried across dangerous Red Sea routes, unloaded and processed, and finally redistributed toward the Nile Valley. Every stage required massive coordination across land and sea simultaneously. Even more mysterious is the metallurgical challenge itself. Copper smelting demands temperatures exceeding approximately 1085 degrees Celsius, and achieving such heat consistently in coastal desert conditions would have required carefully engineered furnaces, continuous airflow management, charcoal production, and stable fuel supplies. Archaeologists discovered traces of industrial firing and metallurgical activity, but the full scale of production remains debated. The fuel problem alone creates major questions. Large-scale copper production consumes enormous quantities of charcoal, and experimental reconstructions suggest ancient smelting operations could require several kilograms of charcoal for every kilogram of usable copper produced. However, the Red Sea coast surrounding Ain Sukhna contains limited natural wood resources. Researchers therefore believe timber and charcoal may have been imported from the Nile Valley, implying a supply chain of enormous complexity operating more than 4 millennia ago. Some historians now argue that Old Kingdom Egypt functioned less like a simple agricultural kingdom and more like a highly centralized industrial economy capable of coordinating mining, metallurgy, transportation, storage, and maritime logistics simultaneously. The implications are enormous because if Egypt truly maintained industrial copper networks on this scale during the Pyramid Age, then the technological infrastructure supporting monuments like Giza may have been far more sophisticated than traditionally acknowledged. Another remarkable discovery at Ain Sukhna involved inscriptions and sealings connected to royal expeditions. These records documented expedition leaders, labour organisation, supply movements, and transportation activity, preserving evidence of an ancient administrative system already operating on a surprisingly advanced level. Large engineering projects do not rely only on tools, but also on logistics, accounting, storage management, and labour coordination. Ain Sukhna suggests that Old Kingdom Egypt may have possessed a far more sophisticated bureaucratic infrastructure than historians once believed, with some researchers comparing its organisational complexity to much later empires such as Rome or Persia. Do you think ancient civilizations were far more technologically organised than modern history admits? Or are sites like Ain Sukhna simply the result of massive human labour and forgotten engineering methods? Share your thoughts in the comments below.